A visitor in the dark, long before astronomers assigned it a name, long before data streams painted its silhouette across Earth's observatories. The object that would later be called 3I Atlas moved with a silence that felt almost ancient. It approached the solar system from a direction that revealed nothing familiar, sliding through the interstellar dark like a memory from a forgotten age. There are countless fragments crossing the sun's domain every year, fragments of rock and ice that have circled our star since the era of planetary birth. This one was different. Its velocity was too great, its geometry too clean, and its trajectory carved a shape that did not belong to anything born among the planets. To the few who would later study it closely, it felt less like an object entering the solar system, and more like a question carried on a path that had taken millions of years to form. As the comet drifted inward, the solar wind wrapped around it and revealed a surface colder than deep space. It did not shimmer with the early signs of sublimation that ordinary comets carry as they warm. Instead, it remained perfectly muted. The first photons of sunlight that touched it seemed to fall away as if absorbed by material that had never known light at all. Even at great distance, it gave off a sense of restraint as though conserving something. A small cluster of automated telescopes in Hawaii registered the faint streak first. Algorithms flagged it. Nothing about its brightness curve made sense. That faint streak stretched across the sensor with uncanny steadiness, told a story of a traveller that had wandered far beyond the cradle of stars that shaped human understanding. When astronomers finally turned trained eyes toward it, they realized the object approached with a speed that did not match anything gravitationally bound to the sun. It was an exile, a visitor, that originated in a different stellar neighborhood, carrying with it the imprints of foreign chemical processes and the gravitational histories of places humans had never seen. The universe often appears quiet, yet every so often it offers hints that the vastness surrounding Earth is not empty, but filled with wandering messengers. 3I Atlas was one of them. As it moved, it caught the attention of researchers who remembered the earlier arrival of interstellar objects like 1I Oumuamua and 2I Borisov. Both had unsettled scientists. Both had challenged assumptions regarding planetary systems and the formation of cosmic debris. Yet neither had arrived with the quiet gravity that 3I Atlas carried. The first nights of observation painted a portrait of an object that refused to behave like a comet. Its reflectivity shifted in subtle rhythms that did not match expected rotations. Its faint coma was almost too symmetrical, as though sculpted by processes that resisted solar heating. All of these details blended into something that seemed like a whisper from distant space. Astronomers could only watch, stunned by the sense that this object was not merely passing through. It felt deliberate, although no natural body is deliberate. The mind paints intentions onto mysteries, especially those that drift silently across the sky. As the days passed, its trajectory narrowed toward a point that had not been expected. 3 Atlas would pass near Mars. That realization spread through the global astrophysics community with a mix of excitement and dread. An interstellar comet measuring possibly hundreds of meters across, traveling at extraordinary speed, was about to sweep through the gravitational and magnetic influences of another world. There had never been a close planetary encounter with an interstellar object in the history of observational astronomy. The chance to study it was extraordinary. The possibility of witnessing something unforeseen was even greater. When simulations predicted the exact corridor 3 Atlas would take near Mars, several researchers noticed something unsettling. The comet seemed to be adjusting its path ever so slightly, not by sudden jumps or violent corrections, but by gradual changes in acceleration that no model could account for. Comets do accelerate due to outgassing, but the rate of change for 3I Atlas was too smooth. Nothing about the solar wind at that distance justified the numbers recorded by early spectrographic measurements. Each small deviation carried the implication that an unseen mechanism was at work. Less experienced analysts quickly blamed instrumentation. Veteran astronomers recognized a pattern they had seen before, one that hinted at motion, governed by a complex interior structure, or perhaps by material that interacted with sunlight in ways unknown to ordinary cometary physics. As 3I Atlas approached the orbit of Mars, something else began to trouble observers. Its coma glowed with a faint bluish tint, a tone that suggested ionization at levels too strong for the comet's distance from the sun. The glow thickened rather than thinned as it moved, as if it were feeding on the very energy that should have torn it apart. This glow was not violent. It was elegant and controlled, almost like an atmospheric halo around an exoplanet. When telescopes captured long exposures, the light formed faint concentric layers like ripples frozen in vacuum. The phenomenon left researchers grasping for models that could reproduce the effect, but none succeeded. That was when the philosophical weight of the discovery settled in. Humanity had spent centuries believing that comets were messengers of chaos, omens that streaked across the sky with unpredictable fire. Modern science replaced superstition with measurement, but even measurement has limits. Objects from interstellar space are pieces of other histories. They are shaped by forces no human civilization has yet encountered. When 3I Atlas drifted closer to Mars, astronomers felt the familiar tension between what they knew and what they sensed slipping beyond their understanding. The object seemed quiet, yet everything about it challenged the foundations of comet science. Night after night, telescopes traced its arc, and with each new data set, the mystery deepened. The comet's rotation slowed slightly, almost unnaturally. Its tail flickered in a pattern that defied solar wind predictions. Even the dust streaming from its outer layers behaved with an order rarely observed. If normal comets are chaotic sculptures of ice dust and ancient molecules, 3I Atlas appeared almost intentional in its structure. That impression did not escape anyone who viewed the early images. It was an object shaped by cosmic violence, yet it carried an uncanny symmetry. As the world continued watching, researchers were forced to acknowledge that this visitor might not simply reveal new chemistry or new dynamics. It might expose the limits of human models themselves. Every era of science encounters an object that pushes the boundaries of understanding. Some objects do this quietly yet profoundly, by displaying behaviors that challenge assumptions. 3I Atlas was such an object. It approached Mars without sound, without flare, without any sign of disturbance, yet its presence created a tremor in the collective imagination of scientists. Something had arrived that was older than any memory of the solar system, and as it moved silently past Mars, it seemed to carry with it a truth no one yet understood. In that silence, one realization grew stronger. Whatever 3I Atlas truly was, it had come from a place where the rules are not the same. It was a messenger from a realm beyond familiar gravity, beyond familiar materials, and perhaps beyond familiar physics. As it neared the red planet, Earth held its breath, waiting to witness a moment that could reshape everything known about interstellar travelers. Something about the comet felt like an unanswered question drifting through the cosmos, still wrapped in the darkness from which it came. Whispers from interstellar space. Before the world understood what it was looking at, before any theory attempted to explain its unsettling behavior, 3I Atlas appeared only as a fragile signature at the edge of computational awareness. In the control room of the Atlas survey in Hawaii, a quiet sequence of numbers arrived during a routine sweep of the night sky. Automated software compared the new data against star catalogues, asteroid logs, and known comet paths. What emerged on the screen was a residual streak that refused to match any recorded object. It was faint, almost hesitant, as if reluctant to reveal its existence, yet it carried the unmistakable motion of something crossing the solar system from an origin far beyond the sun's gravitational domain. The survey team, accustomed to sifting through thousands of false positives, saw nothing remarkable at first. Near-Earth objects frequently confuse early algorithms, but when they checked the follow-up frames, the streak persisted with uncanny consistency. Its brightness did not vary as expected. Its shape remained impossibly stable for something drifting through an ocean of solar radiation. In the background hum of servers and quiet machinery, the discovery began as nothing more than an irregularity, a whisper from the cosmic dark. What no one yet realized was that this whisper carried the remnants of a history older than any planet orbiting the Sun. The team sent the coordinates to the Minor Planet Center for immediate confirmation. Within hours, independent observatories around the world aimed their eyes toward the coordinates. Telescopes in Chile and the Canary Islands found the object moving with a velocity that exceeded typical solar system visitors. It approached on a hyperbolic trajectory that could have originated in any corner of the galactic neighborhood. When the velocity calculation completed, it placed the object firmly in the category of interstellar travelers. It was not born here. It had wandered across the void between stars, carrying with it the chemical fingerprints of a world no longer reachable, perhaps even a world long extinct. As more telescopes locked onto it, astronomers began assembling its early light curve. The object oscillated ever so slightly in brightness, a pattern so subtle that only high-precision instruments could detect it. These oscillations implied an irregular shape or slow rotation details that offered early insight into its physical nature. Yet even these small variations carried hints of strangeness. The object's reflective properties did not align with expectations for an icy interstellar comet. It absorbed far more light than it shed. It behaved like a fragment carved from ancient carbon, or some exotic radiation-darkened material hardened by eons of interstellar exposure. The discovery announcement spread quickly across scientific networks. Only 2 previous interstellar objects had ever been confirmed. The first startled the world with its sharp acceleration and unusual geometry. The second returned humanity to the comfort of something more comet-like, although still foreign in composition. The arrival of a third interstellar visitor reignited a sense of cosmic humility. It reminded researchers that the solar system is not a closed sanctuary, but one small chamber in a much larger structure. Material from distant star systems occasionally crosses paths with Earth, offering glimpses into environments shaped by alien gravitational tides and stellar winds. Once early confirmation passed, observatories began to gather more refined measurements. Infrared instruments detected a surface colder than typical interstellar fragments. Most objects heat slightly as they approach the inner solar system. 3I Atlas remained stubbornly frigid. This unusual coldness suggested that its thermal response to sunlight was delayed or suppressed. Scientists debated whether it could be coated in material with an insulating structure, perhaps a type of carbon mesh woven by natural cosmic processes. Whatever the explanation, the comet refused to behave like anything previously observed. These early anomalies sparked philosophical excitement. Humanity has long wondered what lies beyond the sun's gravitational envelope. The discovery of interstellar visitors provided small pieces of worlds that can never be seen directly. Yet even among these fragments, 3I Atlas stood apart. If Umama had challenged assumptions about shape and acceleration, and if Borisov had offered a more familiar compositional signature, then 3I Atlas emerged as an object that held secrets still deeper, wrapped in layers of quiet behavior that left scientists questioning their most fundamental expectations. Around this time, a small group of theoretical astrophysicists began exchanging private messages. They searched for any detail in the object's motion that hinted at non-standard physics. They knew better than to jump to conclusions. There is a long tradition of misinterpreting data from distant faint objects, yet they sensed something different in this new discovery. The object's early trajectory obeyed gravitational rules, but subtle deviations already appeared in the margins of measurement error. These deviations were small and could easily be explained by imperfect data, but they carried a familiar shape that hinted at deeper anomalies to come. Data collected from larger telescopes provided the first high-resolution images of the coma forming around the object. Although barely visible, the coma shimmered with a strange translucence. Cometary comas usually show chaotic structures shaped by jets of gas and dust. This coma appeared unusually uniform, almost spherical. Such symmetry suggested either extremely low activity or a type of outgassing that distributed evenly across the entire surface. Scientists began to speculate that the object might be coated in materials capable of sublimating with remarkable consistency. If true, it marked an unusual evolutionary path for a fragment forged in the violent debris of an alien star system. As the comet closed the distance, researchers realized its path would align closely with the orbit of Mars. It would not collide, but it would pass near enough to fall under the influence of Mars's gravity and magnetosphere. This created a unique opportunity. For the first time in human history, an interstellar object would be studied not only from Earth, but also from instruments orbiting and standing upon another world. Spacecraft already circling Mars, including MAVEN MRO and various landers, could gather data as 3I Atlas swept past. Each instrument capable of detecting charged particles, magnetic fluctuations, or atmospheric perturbations prepared to record the moment. Scientists could hardly contain their anticipation. The possibility of observing how an interstellar fragment interacted with the environmental features of Mars promised to reveal entirely new aspects of its behavior. Would its coma react to the thin Martian atmosphere? Would the dust shed by the comet behave differently under the weak gravitational pull of Mars? Would the object reveal hidden internal structures as it encountered new gradients of sunlight and solar wind? These questions began to circulate through laboratories and observatories worldwide. Meanwhile, the public received the news with a mixture of fascination and quiet unease. The idea of material drifting from distant star systems is poetic yet unsettling. Something older than the solar system was approaching Mars following a path shaped by forces no one understood. The comet became a symbol of cosmic wandering of the unknown carried across generations of stars. It reminded humanity that the galaxy is a place of perpetual motion, a vast arena where fragments of ancient collisions travel immense distances before arriving at the doorstep of a civilization capable of noticing them. As more precise measurements accumulated, astronomers traced the comet's origin back through its hyperbolic approach vector. Its trajectory suggested it had once wandered near a region of the galaxy known for chaotic stellar interactions. This region likely flung the object into deep space millions of years ago. The thought that 3I Atlas had travelled through the galactic medium for so long added a layer of quiet awe. Its surface had endured cosmic rays, dust impacts, and the gravitational fields of countless stars. It had survived conditions that no human artifact could withstand. Now, after such immense travel, it approached Mars like a message carved from time itself. Night by night, the object grew brighter. Observatories refined their models. The path became clearer. Mars would not be a silent bystander. It would become the stage for a phenomenon that would later shake the foundations of comet science. Every astronomer felt it. Something strange rode within that pale glow. They could not yet describe it, but the whisper carried through the data with growing presence. A visitor from interstellar space was approaching, and with its approach came the first hints of a mystery that would ultimately challenge the structure of physical law. The moment of recognition. As data from the first nights accumulated, a subtle tension spread across the astronomical community. Numbers that initially felt like noise began to build a coherent pattern. 3I Atlas was not simply another wandering object illuminated by the sun. Something in its motion contradicted the ordinary rhythm of celestial dynamics. The recognition did not arrive through a single dramatic instant. It unfolded slowly through dozens of independent measurements that converged with uncanny precision. Each new observation placed the comet exactly where it was predicted to be, yet each prediction required increasingly unusual assumptions about its physical properties. The recognition began with a simple calculation of velocity. Interstellar objects are faster than native comets, but 3I Atlas moved with an elegance that made its hyperbolic speed seem almost intentional. The numbers aligned with an origin beyond the sun's gravitational hold, yet the curve of its path suggested a history shaped by forces that could not be traced. Analysts ran simulations in quiet laboratories, watching the digital representation carve a thin arc that carried it not only through the solar system, but also into the space beyond. These simulations revealed something strange. The orbit was hyperbolic, yes, but unnervingly stable. Most interstellar objects display subtle wobbles caused by uneven outgassing or irregular tumbling. 3I Atlas drifted like a needle threading through gravity with unwavering control. This stability caught the attention of researchers at the European Southern Observatory. When they cross-referenced the object's brightness variations with known models of rotation, they found the inferred spin rate to be too slow for its estimated dimensions. A body that size should have displayed more pronounced variations as it turned. Instead, the fluctuations were barely perceptible. It rotated as though time itself had slowed around it. Some speculated it might be a contact binary, or a fractured object held together by gentle cohesion. Others noted that its surface could be coated with dark material that masked deeper irregularities. Whatever the explanation, the numbers refused to align with any familiar pattern. The recognition deepened when infrared observatories revealed its thermal inertia. The comet absorbed sunlight but released heat at a rate inconsistent with known materials. Interstellar exposure can darken surfaces and produce insulating layers, yet even those mechanisms could not fully explain the thermal profile appearing in the data. Several theorists proposed that it might contain a form of compressed carbon structure rarely observed in natural bodies. Others suggested the possibility of exotic dust bonded by high-energy events near a supernova. These early interpretations intrigued astronomers, but provided no definitive explanation. The shift from curiosity to seriousness occurred when ground-based spectrographs attempted to analyze the faint coma forming around 3I Atlas. The comet emitted gases typical of volatile materials, yet the proportions were skewed. Some molecules appeared with abundances far too high for its distance from the sun. Others appeared too low or were completely absent. Most striking of all was the detection of a molecular signature that hinted at complex carbon chains, usually destroyed by long exposure to interstellar radiation. Their survival implied that the object had either been shielded by unusual layers or had spent much of its journey in regions of space unexpectedly calm. Both possibilities unsettled researchers. Neither fit neatly within known astrophysical contexts. Through all of this, something else slowly became clear. The trajectory of 3I Atlas placed it on a path that would bring it into the observational range of multiple Mars missions. When scientists calculated the exact timing of its closest approach, they realized the encounter would allow unprecedented opportunities. Mars would become a canvas against which the comet's behavior could be measured with remarkable clarity. The red planet's orbiters and landers would record the moment with instruments designed for atmospheric and magnetospheric analysis. Never before had humanity been able to observe an interstellar object through the technological eyes of another world. This realization prompted global coordination. Agencies compared schedules, refined observational strategies, and prepared instruments for what would be a once-in-a-lifetime moment. Some researchers hoped the encounter would resolve the ambiguities that surrounded the object's early measurements. Others quietly feared the opposite. If 3I Atlas behaved strangely near Mars, the mystery could deepen to levels that might challenge well-established models of celestial mechanics. As scientists prepared, the general public began to take notice. News outlets highlighted the arrival of an interstellar comet passing close to a neighboring planet. The language used was often poetic, sometimes sensational, but beneath the surface lay a genuine sense of awe. Human culture has always grappled with the presence of cosmic wanderers. In ancient times, comets were symbols of change and upheaval. In the modern world, they became reminders of how small and fragile the solar system remains. The arrival of a visitor forged in the distant chaos of another star system stirred old instincts. It awakened feelings that stretch back to societies that once traced omens across the night sky. The recognition deepened further when astronomers plotted the comet's deceleration profile. Objects on hyperbolic journeys typically slow slightly as they interact with the sun's gravity. 3I Atlas showed something different. The deceleration curve flattened in ways that made little sense. It behaved as though shedding momentum in a controlled manner. Such behavior is not impossible, but it is highly improbable for a natural object drifting freely across space. Some pointed to subtle outgassing that might escape early detection. Others argued that the small deviations could be artifacts of measurement. Yet the pattern lingered in every dataset, quietly persistent. This pattern became the subject of heated debate in several late-night teleconferences among observatory teams. Most participants resisted dramatic interpretations. The history of astronomy is filled with premature conclusions that dissolve when better instruments refine the data. Yet even the cautious voices admitted that something in the data felt unfamiliar. 3I Atlas did not simply move through space. It expressed itself through motion shaped by influences not yet understood. The recognition of this fact left a subtle imprint across the community. It carried the quiet suggestion that the comet might become more than a scientific curiosity. It might become a turning point. As the trajectory model sharpened, astronomers mapped the final approach corridor with precision. The comet would pass behind Mars from Earth's perspective, creating a moment when its light would be filtered through the thin Martian atmosphere. This alignment offered an accidental gift. By studying the brightness variations as 3I Atlas slipped into and out of occultation, researchers could infer the structure of its coma and tail with exceptional clarity. The potential discoveries stirred excitement. The possibility of confronting new physics stirred tension. Both emotions shaped the atmosphere as scientists prepared for the event. In the quiet hours before dawn, as telescopes tracked the visitor through still dark skies, many astronomers felt the weight of recognition settling in. They understood that they were witnessing the early chapters of something extraordinary. An interstellar traveler shaped by forces millions of years removed from Earth's history was approaching Mars. Every measurement drew humanity closer to an encounter that could alter its understanding of how matter evolves in the spaces between stars. The solar system does not receive many visitors from distant regions of the galaxy. When one arrives carrying subtle contradictions in its behavior, the world pays attention. 3I Atlas was no longer just a faint signature on an algorithmic display. It had become a message. It had become a moment. It had become the focal point of a scientific narrative that would unfold with increasing strangeness as it neared the red planet. The recognition was complete. Something unprecedented was approaching Mars, and with its approach came the first undeniable sign that the universe still holds surprises capable of reshaping human understanding. An anomalous pathway emerges. As researchers refined their measurements, the trajectory of 3I Atlas began to reveal subtle departures from the elegant curve predicted by classical celestial mechanics. At first, these departures appeared as tiny deviations tucked into the margins of error, barely noticeable amid the noise of early data. Yet night after night, as more observatories joined the monitoring effort, the deviations persisted with quiet insistence. Each new measurement sharpened the trajectory and revealed a route that seemed shaped by something more complex than gravity and simple outgassing. The earliest hint appeared when a team in Arizona compared two independent tracking sequences. They expected the comet's position to match their simulation within expected tolerances. Instead, it shifted by a fraction that felt too persistent to ignore. The shift did not resemble random scatter. It formed a consistent trend that suggested an influence acting gently on the object, altering its course, as though nudging it along a path not entirely its own. Researchers initially suspected calibration issues in their instrumentation. After several recalibrations, the deviation remained. That persistence drew attention from specialists accustomed to disentangling the delicate balance of forces acting on distant bodies. Meanwhile, a European observatory with access to high-precision astrometric tools performed an independent verification. Their readings aligned with the Arizona results, confirming that 3I Atlas was drifting in a direction slightly offset from its projected path. The magnitude of the drift was small, but the pattern carried a distinct fingerprint. It resembled a controlled acceleration, one that grew more evident over time. A comet propelled by natural processes can exhibit irregular thrust as pockets of volatile material vent and rotate unpredictably. The acceleration of 3I Atlas lacked this chaotic signature. It behaved like a force applied evenly with a steadiness that felt strangely deliberate. As the data accumulated, researchers began to notice something else. The comet's acceleration varied with distance from the Sun in a manner that contradicted typical thermal models. An object warming under solar radiation often displays increased outgassing and therefore increased non-gravitational acceleration. 3I Atlas defied this expectation. Its acceleration followed a smoother gradient that did not match the expected behavior of ice transitioning from one phase to another. Some scientists suggested that the surface materials might be undergoing a form of sublimation unfamiliar to comets in the solar system. Others proposed that the object could be coated in compounds whose thermal properties had been shaped by environments very different from the region surrounding the Sun. The oddities deepened when a research team in Japan reanalyzed the brightness curve. Instead of fluctuating in ways consistent with jets erupting from specific surface regions, the brightness remained unnaturally stable. This stability created an enigma. If outgassing were responsible for the comet's controlled acceleration, it should have produced visible changes in brightness. Without these changes, the explanation required an even layer of sublimation spread across the entire surface. Such a phenomenon, while theoretically possible, has rarely been observed. It suggested a body with an unusually homogeneous composition, one that might have formed under conditions no longer common in the modern galaxy. Instruments tracking the Comet uncovered another perplexing detail. The gases surrounding 3I Atlas exhibited a faint asymmetry, yet the direction of this asymmetry did not match the direction of its acceleration. In typical comets, gas jets act like miniature thrusters, creating movement in the opposite direction of the ejected material. Here, the vector relationship did not align as expected. The gas flow followed one orientation, while the trajectory shift leaned slightly elsewhere. Several teams attempted to model this divergence. Some speculated that the gas was being deflected by magnetic interactions with the solar wind. Others suggested that internal cavities within the comet might produce complex flow patterns that disguised the true direction of thrust. Yet each model left small but significant inconsistencies unresolved. The situation became even more intriguing when the first gravitational simulations were run using all available data. The comet's path did not follow the clean hyperbolic escape expected of an object passing through the inner solar system. Instead, its curve bent with a softness that suggested slight variations in momentum transfer. When researchers compared the movement of 3I Atlas to the trajectories of previous interstellar visitors, they noticed that its behavior diverged from known patterns. Oumuamua displayed erratic acceleration linked to spectral anomalies. Borisov behaved like a classic comet shaped by foreign chemistry. 3I Atlas fell into neither category. Its deviations were too orderly to be chaotic, yet too inconsistent to follow simple natural processes. A group of dynamicists from South America examined the object's motion using advanced numerical integration methods. Their final report noted that the deviation could not be fully attributed to radiation pressure, nor to dust interactions, nor to any conventional mechanism likely to be encountered within the solar system. According to their interpretation, the force influencing 3I Atlas might originate from an internal distribution of mass capable of shifting over time. If the comet carried deep fractures or layered structures, small internal movements could in theory alter its moment of inertia and produce changes in trajectory. Such processes have been discussed in the context of asteroid physics, but the level of precision seen here appeared far beyond what internal rearrangements could ordinarily produce. The notion that 3I Atlas might contain internal structures unlike those of typical comets began to inspire new speculation. Perhaps it formed in a region of space with extreme temperature fluctuations. Perhaps it inherited layered materials from a parent body that experienced violent stellar events. Some researchers even considered whether the comet passed near a region of dense molecular clouds that could have altered its composition in exotic ways. Each hypothesis attempted to respect known astrophysics while acknowledging the strange elegance of the trajectory shifts. None of them offered a complete explanation. The scientific world began to sense that the deviations were not random accidents of measurement. They revealed themselves too consistently across instruments, too persistently across nights, and too cleanly across international collaborations. When astronomers plotted the accumulated deviations on a single graph, the trajectory formed a gentle curve that diverged from the projected line by a measurable distance. The divergence was small enough to avoid alarm, but large enough to demand the attention of theoreticians who recognized the significance of even the smallest gravitational anomalies. As the comet moved closer to Mars, the deviations began to increase slightly. Instruments that tracked the coma noted alterations in shape that aligned with the trajectory change. Advanced computer simulations revealed a delicate dance between the comet's motion and the subtle influence of the solar wind. Some interpretations proposed that the object might be interacting with charged particles in an unusual manner. Perhaps the materials coating its surface carried electrical properties uncommon among solar system comets. The possibility intrigued specialists in plasma physics, who wondered whether 3I Atlas might be behaving like a natural conductor, drifting through a charged environment. This possibility gained support when MAVEN mission teams prepared to monitor the comet as it approached the Martian magnetosphere. The subtle deviations hinted that the object might respond to magnetic gradients with greater sensitivity than expected. Such sensitivity would be unusual for a natural body lacking significant electrical conductivity, but not impossible for interstellar fragments shaped by unknown environments. The thought that Mars might reveal even deeper complexities heightened anticipation among researchers watching the object's approach. The scientific community had not reached consensus, but a quiet shift had begun. 3I Atlas was no longer merely an interstellar traveler passing through. It had become a source of profound questions about how matter behaves in the vast spaces between stars. Its anomalous pathway suggested influences hidden beneath the surface interactions waiting to be uncovered, and perhaps hints of physical processes not yet fully understood. With each new deviation, the sense of approaching revelation grew stronger. Mars awaited. The mystery deepened. The pathway of 3I Atlas continued to carve its elegant curve through space, leaving behind a trail of questions that demanded answers. Mars Encounter begins. As 3I Atlas continued its steady glide toward the orbit of Mars, the network of observatories around Earth refined its trajectory with increasing precision. The mysterious object had already shown tendencies that defied expected cometary behavior, but it was the nearing encounter with the red planet that promised the first decisive clues. Mars, unlike Earth, lacked a dense atmosphere that could mask delicate interactions between the comet and its surroundings. It offered a clean backdrop, a quiet world with only a whisper of air and a patchwork of magnetic anomalies scattered across its crust. For the scientific community, the approaching moment felt like the opening of a door. The first spacecraft to sense the coming presence of 3I Atlas was MAVEN, orbiting high above Mars to study the planet's thin upper atmosphere and magnetosphere. MAVEN's instruments were designed to detect changes in charged particles, magnetic gradients, and atmospheric escape processes. As the comet drew nearer, the spacecraft began to register faint irregularities that did not align with typical solar activity. These irregularities were subtle, almost shy, but they appeared repeatedly at the edge of the detection threshold. Analysts examined them with care, verifying calibration, removing noise, comparing patterns to archived solar data. After several cycles of elimination, the irregularities remained. Their timing matched the comet's approach. Far below, MAVEN, the Mars Reconnaissance Orbiter, prepared its suite of instruments to capture the passing visitor. Its high-resolution cameras would study not body structure but coma formation and dust dynamics against the darkness of space. Meanwhile, orbiters from previous missions stood ready to provide additional geometric viewpoints. These multi-angle observations would allow researchers to reconstruct the comet's behavior in 3 dimensions. It was rare for so many instruments to be perfectly positioned to observe a single phenomenon simultaneously. For interstellar objects, it was unprecedented. On Earth, research teams realized that the Mars encounter would allow them to measure how the comet's faint outer layers responded to the planet's gravity and thin atmosphere. If 3I Atlas carried volatile materials with low binding energies, they might glow more brightly as the comet skimmed the subtle warmth radiating from the Martian surface. If the comet possessed unusual electromagnetic properties, the localized magnetic anomalies beneath Mars's crust might reveal them. Scientists began planning cross-missions analyses comparing MAVEN particle readings with orbiter imagery and Earth-based spectroscopy. The level of coordination reached a scale typically reserved for major planetary events. As the comet approached its closest distance to Mars, strange fluctuations grew more pronounced in data streams from MAVEN's magnetometer. These fluctuations did not resemble the signatures of solar storms or routine interactions between Mars and the solar wind. They fluctuated in slow rhythmic intervals that carried a structure unlike ordinary noise. Some analysts suggested they might originate from the interference patterns created as the comet's coma intersected the flow of charged particles passing around the planet. Others proposed that the comet could be releasing ions at a rate not previously detected during its earlier approach. Even these possibilities did not fully explain the patterns, but they offered practical starting points for investigation. Within days of the closest approach, the first high-resolution images of 3I Atlas near Mars began to arrive. To the surprise of mission scientists, the comet's coma brightened slightly as it entered the region influenced by the planet's magnetic anomalies. This brightening happened not at the moment of closest gravitational interaction, but a short distance before, as if the comet were responding to conditions ahead of it. This timing left many researchers puzzled. Most comets react to heating or direct solar pressure, not to invisible gradients in a planet's magnetic crust. Yet the brightening was unmistakable, and it grew in intensity with an elegance that did not resemble typical dust eruptions. The behavior became even stranger as the comet moved into Mars's shadow. Under ordinary circumstances, a comet passing behind a planet should dim sharply. Without sunlight, the coma cools and contracts, scattering less light. But as 3I Atlas entered the shadowed region, its brightness increased instead of fading. Orbiting instruments watched the glow swell with soft radiance like embers fed by a hidden breath. Analysts searched for potential explanations. One idea proposed that the sudden absence of solar radiation could have allowed trapped volatiles to release in a burst. Another idea suggested that electrons accumulated on the comet's surface might have recombined in the dark, creating a brief upsurge in luminescence. Both ideas offered partial explanations, yet neither accounted for the sustained and smooth brightness increase that occurred. Earth-based observatories captured the same phenomenon from afar. As the comet hid behind the planet, the glow did not vanish. Instead, a halo of light wrapped around the region where the comet should have been. That halo expanded slowly as though responding to an unseen field. Some specialists wondered whether Mars's exosphere could be interacting with the comet's gas stream in ways never observed before. The exosphere is thin, but its charged particles can create faint auroral effects under the right conditions. Perhaps the comet-bearing material shaped by interstellar travel produced interactions that resembled miniature auroras. The thought intrigued plasma physicists who had long considered the possibility that interstellar comets might carry unique electrical properties. As the comet re-emerged from Mars's shadow, the glow receded with a gentleness that left analysts captivated. There were no sudden transitions. Every change seemed smoothed, as if shaped by a process finely tuned by some hidden variable. The brightness did not return to its earlier baseline. It remained slightly elevated, as though the encounter had awakened something within the object. This subtle enhancement added a new layer to the mystery already surrounding 3I Atlas. The comet had behaved in a way that diverged from every known case of planetary shadow passage. Meanwhile, MAVEN detected a burst of charged particles near the comet's path, a burst that reached levels above typical background counts, but displayed no characteristics of a solar event. The timing correlated precisely with the moment of maximum brightness increase. This connection sparked immediate discussion among teams collaborating across continents. Some believed the comet's materials might be interacting with Mars's magnetic anomalies, releasing energetic particles. Others suggested complex ionization dynamics at the boundary of the comet's coma. The phenomenon did not fit neatly within any established framework, yet it could not be dismissed. The data was clear. A further surprise arrived when MRO's spectrometer captured unusual signatures in the dust cloud surrounding the comet. These signatures hinted at chemical bonds rarely detected in typical comets. A set of compounds appeared that would ordinarily break apart under prolonged exposure to cosmic radiation. Their presence in 3I Atlas implied a protective layering or internal structure capable of shielding delicate molecules during interstellar travel. That implication led to new questions regarding the internal architecture of the comet. Perhaps it harbored nested layers of material. Perhaps it encased fragments of older formations from distant star systems. By the time 3I Atlas left the immediate vicinity of Mars, the scientific world was no longer studying a comet. It was studying a contradiction. The Mars encounter had transformed a curious interstellar visitor into a genuine enigma. Every instrument that observed it recorded something that resisted straightforward interpretation. The comet accelerated in ways that defied conventional models. It brightened in shadow. It interacted with charged particles as if sensitive to fields no ordinary body should detect. It scattered molecules that should not have survived its journey. Through all of this, the object moved with serene steadiness as if unaware of the cascade of questions it had created. The Mars encounter marked a turning point. What had begun as a whisper in the data now spoke in clear, measurable signs. 3I Atlas behaved according to rules not yet incorporated into the language of comet science. With the red planet behind it and deeper mysteries ahead, the comet continued on its path, weaving a question into the fabric of the solar system that no one yet knew how to answer. A strange acceleration. As 3I Atlas drifted beyond the immediate sphere of influence around Mars, the scientific community expected the comet's behavior to settle into predictable patterns. The encounter had already produced enough anomalies to occupy researchers for years, but many assumed that once the object left the unusual environment shaped by the planet's weak magnetic anomalies, it would resume a more conventional course through interplanetary space. Instead, the comet began to accelerate again, and this acceleration followed no established profile. The first indication of renewed acceleration appeared in data from a French observatory that had been tracking the comet nightly. Their automated reduction pipeline flagged a small difference between the predicted and observed positions. The difference was minute, far smaller than the drift recorded during the early phase of its approach toward Mars, yet its timing raised immediate attention. Such acceleration typically occurs when a comet heats from solar radiation and vents new jets of gas. But at this distance from the Sun, the thermal environment remained too mild to trigger sudden outgassing. The observed shift seemed to arise from a different, more elusive cause. Within days, observatories in South Africa, Australia, and the United States confirmed the same acceleration pattern. It was gentle, but steady, consistent, but not chaotic. The smoothness of the acceleration drew immediate contrast with the irregular bursts seen in typical cometary jets. This pattern did not display jitter or flicker. It moved with a quiet, controlled increase, almost as though responding to an unseen gradient. Specialists in non-gravitational forces examined the data and compared it to known models of dust jetting, solar radiation pressure, and thermal lag. None of these mechanisms aligned with the behavior observed. To rule out instrumental bias, several observatories ran synchronized observations, adjusting for parallax and varying atmospheric conditions. The results aligned across multiple nights. They depicted a comet subtly but undeniably increasing speed. The acceleration curve formed a gentle arc that resisted simple classification. A few researchers proposed that the encounter with Mars might have altered surface conditions, exposing new layers of volatile material. If this were true, increased sublimation might explain the shift. However, infrared analysis offered no evidence of significant temperature change along the comet's surface. The thermal signature remained muted, as if the object refused to warm despite its growing proximity to the Sun. A compelling clue emerged when a research group at the University of Toronto analysed the acceleration timing in relation to subtle changes in the comet's tail. They discovered that the tail's orientation shifted slightly in the hours following the Mars encounter. This shift did not correlate with solar wind conditions at the time. Instead, the gas stream bent toward a direction that could not be explained by radiation pressure alone. The alignment suggested that the comet's acceleration might be influenced by internal factors, perhaps linked to structural or compositional changes occurring beneath the surface. This hypothesis intrigued theoreticians who studied the physics of interstellar bodies. A layered or porous internal structure could in theory create delayed or distributed sublimation effects that mimic non-gravitational propulsion. Yet even these ideas face challenges. For such internal processes to produce acceleration of this magnitude, the comet would require a level of structural stability not commonly found in long-travelling interstellar fragments. Most such fragments endure intense collisions, thermal shocks, and radiation exposure that leave them fragile, fractured, or irregular. 3I Atlas displayed none of the erratic tumbling associated with such damage. Its rotation remained slow and graceful, its brightness curve unusually stable. This combination of steadiness and acceleration created a tension that puzzled researchers around the world. To explore alternative explanations, astrophysicists turned to numerical models that incorporated microstructural changes within the comet's nucleus. Some simulations attempted to reproduce the observed speed by assuming deep ice reservoirs that began venting long after the Mars encounter. Others explored whether the comet might contain exotic materials shaped by chemical reactions rare in the solar system. These simulations produced partial matches, but left important discrepancies unresolved. The uniform acceleration persisted as a key point of confusion. The mystery deepened when new spectroscopic data arrived from an infrared observatory in Chile. The analysis revealed a subtle enhancement in certain molecular emissions that had not been present before the Mars encounter. These emissions suggested that fresh material was indeed being released from the comet's surface. However, the rate of release did not match the observed acceleration. The chemical output was too weak to produce a change in momentum of the magnitude recorded. This discrepancy unsettled researchers. If the outgassing was not strong enough to account for the acceleration, another force had to be acting upon the object. In search of further clarity, scientists examined the relationship between the acceleration and local variations in the solar wind. Data collected by space weather monitoring satellites indicated that the comet moved through a region where the particle environment had shifted. But the timing did not coincide cleanly with the acceleration curve. The solar wind flowed with its usual unpredictability, yet 3I Atlas responded as though sensing a different set of conditions altogether. Some specialists in heliophysics proposed that the comet's materials might interact with the solar wind in a highly unusual manner. If the comet carried compounds capable of charging or discharging under specific electromagnetic conditions, this could influence its motion. Such interactions have been theorized in rare cases but never confirmed through observation. Meanwhile, high-resolution imaging revealed that the comet's coma had expanded in a strangely symmetrical pattern. Comas typically grow with uneven boundaries shaped by jets and chaotic dust movement. The coma of 3I Atlas expanded like a sphere expanding from an internal pulse, smooth and almost perfectly radial. This symmetry fascinated researchers who studied fluid dynamics in space environments. It implied a release mechanism more uniform than any previously documented. If the acceleration originated from such a mechanism, it suggested that the comet's inner layers might be responding in a coordinated manner. Yet nature does not typically favor coordination in bodies wandering through interstellar space. Another layer of complexity emerged when MAVEN transmitted additional observations recorded during the comet's departure. The spacecraft detected slight fluctuations in the charged particle environment trailing behind the comet. These fluctuations aligned with the new acceleration phase. The particles formed faint streams that moved in parallel with the comet's direction of travel. This discovery inspired discussions regarding whether the comet might be creating electromagnetic fields strong enough to influence its own motion. Such fields would require internal processes unlike any observed in ordinary comets. Some theoretical physicists speculated about piezoelectric effects, crystalline structures capable of generating charge under pressure, or even remnants of magnetized materials inherited from the comet's parent star system. These interpretations remained speculative, yet each opened possible avenues for inquiry that extended beyond the usual boundaries of comet science. The growing number of unexplained variables raised a quiet realization among researchers. 3 Atlas was revealing not a single anomaly, but a pattern of interconnected mysteries. Its behavior before and after the Mars encounter appeared linked by mechanisms not yet understood. The acceleration was not an isolated event. It was part of a sequence, a gradual unfolding of phenomena that pointed toward a deeper and more complex underlying structure. As the comet accelerated, it left behind a trail of questions that expanded almost as quickly as its coma. Why did the acceleration begin precisely when it did? What internal processes could maintain such smooth motion? Why did the thermal profile remain unchanged? Could the interaction with Mars have triggered a phenomenon stored within the comet's structure for millions of years? Or was the comet responding to environmental conditions in a way that no current model could predict? These questions hung over the scientific community like a mist. There were no quick answers, only growing awareness that the interstellar traveller had entered a new phase of behaviour. From Earth, from Mars' orbit, and from deep space instruments, the acceleration of 3I Atlas was recorded with increasing clarity. What it meant remained uncertain, but the message carried through every data stream. The comet moved with purpose not seen in nature. The mystery had begun to expand. Threads of the impossible. The deeper astronomers examined the motion of 3I Atlas, the more its trajectory began to resemble an unresolved equation written across the sky. The comet no longer behaved like an object merely drifting under the influence of gravity and sunlight. It responded to its surroundings in ways that challenged the most familiar expectations of cometary physics. Every new data point seemed to draw a thin thread between observable facts and something that lay just beyond interpretation. Those threads began to weave a pattern that felt increasingly improbable. The first sign that the comet had entered a new phase appeared when high-precision tracking arrays detected a fractional wobble in its projected course. The wobble was too orderly to be attributed to measurement noise. Instead, it traced out a curve that repeated with surprising consistency. Some analysts suggested that the wobble might reflect a subtle shift in internal mass distribution. Others speculated about complex outgassing concealed beneath layers of darkened material. Yet even preliminary comparisons between the wobble and the comet's rotation revealed that the two did not align. If the wobble were caused by internal dynamics, it should have synchronized with the rotation, or at least shown some predictable correlation. Instead, it moved with an independent rhythm. This independence puzzled specialists who built dynamical models of small bodies. The wobble did not appear random. Its recurrence hinted at an underlying influence that did not fit conventional predictions. Current computational frameworks attempted to simulate microjets or thermal pockets that might produce regular impulses, but these simulations produced chaotic patterns rather than the refined periodic curve seen in the data. The mismatch underscored a growing problem. The comet's motion contained a structure that resisted natural explanation. At the same time, telescopes measuring reflected light discovered faint oscillations in brightness that did not match known scattering effects. These oscillations occurred with a periodicity that differed from the one linked to the object's rotation and also differed from the wobble. This created a second rhythm layered atop the first, as if the comet were expressing multiple hidden cycles at once. Observers found themselves charting these cycles like astronomers of earlier centuries charted the pulse of variable stars. Yet unlike stars whose rhythms spring from internal fusion and predictable physics, the oscillations within 3I Atlas appeared as if shaped by external conditions interacting with unknown materials. The mystery deepened when a research group in Italy identified subtle shifts in the phase of these oscillations. These shifts coincided with slight changes in the solar wind environment, but the correlation was too weak to be framed as a direct cause. The comet responded as though sensitive to influences far more nuanced than the usual push of charged particles. Some interpretations entertained the possibility that the surface materials of 3I Atlas possessed uncommon conductive properties. If true, these properties might allow the comet to experience electromagnetic forces stronger than those affecting typical cometary nuclei. However, infrared spectroscopy yielded no clear evidence of metallic compositions or mineral structures capable of such enhanced interactions. During this period, the expansion of the comet's coma revealed further irregularities. Instead of expanding outward in a uniform glow, the outer layers exhibited faint ripples that passed through the dust cloud in smooth concentric waves. These ripples lacked the randomness seen in gas outbursts or dust jets. Instead, they formed evenly spaced arcs reminiscent of interference patterns. Analysts studying fluid dynamics in low-pressure environments attempted to model the arcs using temperature gradients, sublimation fronts, and dust collisions. None of the models reproduced the symmetry observed around 3I Atlas. The ripples persisted as a quiet signature of some deeper mechanism shaping the coma. At the same time, instruments aboard orbiters near Mars detected faint perturbations in the charged particle environment, trailing behind the comet. These perturbations extended farther than expected and displayed a level of coherence rarely seen in the wake of natural bodies. The turbulence of particle streams typically breaks apart quickly, yet the stream behind 3I Atlas retained its order as if guided by an internal field. Analysts examined potential explanations ranging from induced magnetism to electrostatic structures built from accumulated charge. These explanations offered partial insight, but still left gaps. The field appeared too stable for static charge and too subtle for an intrinsic magnetic core. Meanwhile, several computational astrophysics teams compared the comet's acceleration curve to known patterns produced by solar radiation pressure. The comparison revealed that radiation pressure alone could not account for the observed trajectory. Even models that assumed exotic low-density materials failed to replicate the acceleration profile. When teams examined whether small fragments breaking off the nucleus might impart additional momentum, they found no evidence of fragmentation in the imagery. The nucleus remained intact and unbroken, shining as a single point against the dark. The absence of fragmentation raised further questions when researchers studied the symmetry of the dust tail. Under typical conditions, dust tails curve in predictable arcs shaped by the sun and the motion of the comet itself. 3I Atlas produced a tail, with astonishing steadiness, a thin ribbon that refused to twist or kink. The tail did not behave like a passive stream of dust. It aligned itself in a manner that suggested underlying order. This quality inspired discussions about whether particles lifted from the nucleus might be interacting with an invisible structure or force. One of the most perplexing findings came from a comparative analysis of ultraviolet and visible light measurements. Ultraviolet signatures indicated the presence of high-energy molecules that should have decayed more quickly under solar illumination. These molecules persisted longer than expected, maintaining brightness, despite exposure to radiation intense enough to break them apart. This persistence suggested that the molecules were being replenished or shielded. However, the shielding mechanism remained hidden. The comet appeared to preserve rare molecules with an efficiency that exceeded standard chemical expectations. While these observations circulated through research networks, a different line of evidence emerged from long baseline interferometry. Using widely spaced observatories, scientists created composite signals that tracked minute shifts in the comet's position. The resulting data revealed faint distortions that did not resemble gravitational influences from nearby bodies. These distortions were not strong enough to imply dramatic physics, but subtle enough to provoke curiosity. The pattern appeared as though the surrounding region of space was slightly shaped or warped near the comet. The possibility stirred interest among specialists familiar with how charged plasma can create refractive effects, yet the distortions did not align with typical plasma signatures. These combined anomalies pushed some researchers to explore non-traditional frameworks. A small group considered whether the comet might contain materials capable of interacting with quantum vacuum fluctuations in ways not yet tested in laboratory conditions. Another group examined whether the comet's long interstellar journey through regions of varying density could have structured its internal layers into exotic configurations. Neither idea sat comfortably within established theory, but both acknowledged the growing complexity that standard explanations struggled to address. As more data poured in, the scientists involved in the observations began to sense a quiet shift in perspective. The comet's behavior no longer resembled a series of separate oddities. Instead, these oddities connected, forming a tapestry of phenomena that seemed to share underlying roots. The acceleration, the ripples in the coma, the steady tail, the oscillations in brightness, and the distortions in position suggested that the comet might possess properties shaped by conditions not found within the solar system. It was not that the comet broke physical laws, rather it followed laws whose parameters had not yet been encountered. The solar system's comets taught one set of lessons. This traveller shaped by regions of space far from the sun's influence offered another. Every passing hour deepened the sense that 3I Atlas might hold clues to processes that operate across cosmic distances, yet leave only faint traces detectable by human instruments. The scientific world had not reached any consensus. Yet it was clear that the comet's motion, once thought to be a simple passage through the inner solar system, now represented something much more intricate. The threads of the impossible began to intertwine. A mystery was taking form not in sudden revelations, but in patterns that refused to fit the boundaries of the familiar. The coma that shouldn't exist. As 3I Atlas journeyed deeper into the inner region of the solar system, telescopes trained on the object began reporting an unsettling development. The coma, which had already displayed signs of unusual symmetry during earlier observations, now expanded in a manner that contradicted both expectation and precedent. Under normal circumstances, a comet's coma grows when solar heat liberates volatile ices from the nucleus, creating a cloud of gas and dust. The speed of expansion follows patterns shaped by temperature composition and rotation. But the coma around 3I Atlas grew with an elegance that defied all known thermal responses. It did not erupt or fluctuate. Instead, it unfolded with a calm precision that suggested a mechanism fundamentally different from sublimation alone. The first detailed analysis came from a group of researchers using a telescope array in Chile. Their imaging revealed layers of material extending outward in perfect gradients, free from the jagged structures that usually mark the influence of chaotic dust streams. Each layer glowed faintly, forming a halo that wrapped the comet like a shell carved out of mist. This shell did not resemble the diffuse clouds seen in typical comets. It held itself together with a cohesion that resisted easy interpretation. Early comparisons with other interstellar objects proved unhelpful. Neither of the two previously recorded interstellar comets exhibited anything similar. Scientific interest sharpened further when spectroscopic readings revealed that the coma contained a surprising ratio of molecules rarely detected in large concentrations around natural bodies. These molecules, fragile by nature, should have broken apart during the comet's long journey through the interstellar medium. Yet they appeared here in abundance, almost as if preserved inside protective chambers, until the moment they were released. Some specialists noted that their presence hinted at a complex internal structure, capable of shielding delicate compounds from the harsh environment between stars. This inference carried implications that stretched far beyond ordinary cometary science. Another perplexing feature emerged when instruments recorded the distribution of dust grains within the coma. Instead of following the expected outward slope, dust density remained strangely consistent across large segments of the cloud. This uniformity created a soft, almost glowing smoothness that struck observers as unnatural. Dust streams typically fade with distance from the nucleus, broken apart by particle collisions and solar forces. But the coma surrounding 3I Atlas maintained its density as though replenished by a continuous, evenly distributed flow. Some researchers wondered whether the comet held reservoirs of material beneath its outer layer that emitted dust in a perfectly controlled manner. This idea, however, met resistance when scientists compared dust velocities at different distances. Dust near the nucleus travelled at speeds similar to that of ordinary comets, but dust farther out moved faster than expected. The increase in speed did not match any known sublimation pattern. Instead, it suggested the presence of a faint outward push. That push was not strong enough to classify as jet. It acted more like a whispering force guiding dust outward with unusual consistency. Specialists in microgravity dust dynamics examined this pattern closely. They attempted to model the push as a product of low-level gas pressure or electrostatic charge. Their models captured fragments of the behavior but failed to replicate the full effect. Meanwhile, astronomers analyzing light scattering observed that the coma exhibited an unusual transparency. Typical comas scatter and absorb light irregularly due to dust clumping and chaotic particle orientation. The coma of 3I Atlas scattered light with a clarity reminiscent of fine crystalline particles. Some wondered whether the dust grains possessed unique shapes formed under exotic astrophysical conditions. Such shapes could influence how light passed through the cloud, creating the ethereal clarity recorded in observational data. But again, no single explanation accounted for the full suite of phenomena. At the same time, UV measurements detected faint emissions that formed alternating rings within the coma. These rings resembled concentric layers, as if the coma were composed of pulses emitted in cycles. The periodicity of these pulses matched neither the comet's known rotation nor its acceleration profile. It introduced a third cycle, independent of the others, hinting that multiple internal processes might govern the behavior of the nucleus. Observers who studied the rings speculated that they could be remnants of thermal layers or pressure waves formed under conditions unlike anything encountered in comets shaped within the solar system. In parallel with these findings, deep space antennas tracking the comet's position noticed slight fluctuations in signal strength when transmissions passed near the coma. These fluctuations suggested that the coma's density and ionization varied in small but structured patterns. The structure did not reflect the expected randomness of dust clouds. Instead, it indicated pockets of gas or dust arranged in a way that implied a degree of organization. Analysts tried to correlate these pockets with solar activity, yet no match emerged. The patterns maintained their shape independent of changes in the heliosphere. Further confusion arose when planetary scientists examined how the coma responded to different angles of sunlight. Under ordinary conditions, sunlight streams through a comet's coma, unevenly creating bright regions where dust thickness is highest. But in the case of 3I Atlas, illumination spread evenly across the entire cloud. This uniformity suggested that the coma possessed optical properties not seen in typical comets. Some theorists proposed that the dust grains might contain refractive elements capable of bending light in unexpected ways, creating the illusion of even distribution. Others considered whether the cloud structure itself could be so uniform that sunlight simply passed through it without creating shadows or clusters. A breakthrough of sorts emerged when a research team in Germany compared the Comet's spectral profile to a database of extraterrestrial organic compounds. They found faint signatures that hinted at long-chain carbon structures uncommon in solar system comets. These structures often break apart under extreme conditions, yet here they were present and stable. If the nucleus preserved them throughout its interstellar journey, it suggested that the comet had passed through regions where such molecules formed and survived. Perhaps the comet originated near a young star, rich in complex organic chemistry. Perhaps it drifted through a molecular cloud thick with carbon chains. Whatever the source, the molecules added another layer of wonder to the growing mystery. The mystery deepened further when computational models attempted to reproduce the comet's perfect circularity. Most models predicted distortions as the comet interacted with the solar wind, but the observed coma refused to bend or twist. It held its shape with quiet resilience as though insulated from external forces. This resilience drew the attention of plasma physicists who wondered whether the comet's coma might be interacting with the solar wind in an unusual way that preserved its geometry. Perhaps ions released by the comet formed a boundary layer strong enough to stabilize the cloud. This possibility, however, required physical conditions not yet observed in natural objects. Even more perplexing was the discovery that the coma's intensity increased slightly during periods when solar wind density dropped. The relationship suggested that the comet might be responding inversely to environmental pressure expanding when the surrounding space grew quieter. This behavior contradicted typical thermal and chemical reactions. It hinted at a deeper process controlling the coma's growth, one that remained invisible to current analytical methods. Throughout these investigations, the object continued its steady movement, as if indifferent to the storm of questions surrounding it. For observers on Earth and in orbit around Mars, the most striking feature remained the coma's quiet perfection. It did not flicker. It did not distort. It expanded like a slow breath held for millions of years and released into the solar system with unnerving grace. The coma that should not exist existing with impossible elegance became a symbol of the deeper mystery that lay at the heart of 3I Atlas. A mystery not yet articulated but felt in every dataset. A mystery pointing toward a nucleus shaped by forces far stranger than those known to the planets orbiting the Sun. A tale against all logic. As 3I Atlas progressed along its inward path, observers expected its dust tail to behave like the tails of all known comets. Solar radiation pressure should have pushed dust particles away from the Sun, shaping a long plume that stretched outward into space. Instead, the dust tail of 3I Atlas defied this foundational expectation. Instruments across several continents began reporting that sections of the tail bent in a direction that contradicted the geometry dictated by sunlight. It did not swing away from the Sun as physics predicted. At times it angled partially toward it as though influenced by a force acting inward rather than outward. The earliest indication of this disturbing behavior arrived from a set of images captured by an array in the Canary Islands. When the astronomers compared sequential exposures, the curvature of the tail appeared subtly reversed. They hesitated to believe the result. Atmospheric conditions can distort long exposure images, but after careful correction the anomaly persisted. The tail deviated from the expected arc with a consistency that demanded closer scrutiny. Multiple teams ran computational image enhancement on the data. The refined images painted the same unsettling picture. The curve leaned toward the Sun in places where it should have leaned away. A few hours later, data from Chile independently showed the same reversal. The alignment could no longer be dismissed as error. The dust tail behaved as if guided by a field with no clear origin. Researchers tracking the speed of dust grains noted another surprising detail. Dust closer to the nucleus followed a path consistent with solar forces, but dust farther away drifted along lines that contradicted even the most flexible interpretations of radiation pressure. This drift formed smooth arcs, almost like the graceful sweep of a ribbon caught in an invisible tide. The scientific community struggled to find explanations that matched the observational results. Some analysts explored the possibility that the comet had passed through an unusual pocket of electrically charged particles. If the dust grains contained conductive material or carried accumulated charge, they might respond to electric fields rather than sunlight alone. However, tests using variable charge simulations produced outcomes far less orderly than the actual tail. Electric field interactions tend to create turbulent motion, yet the tail of 3I Atlas retained a calm, coherent shape. Another possibility considered whether the comet could be shedding dust particles of extremely low mass small enough for magnetic influences to affect their motion. This line of thought intrigued individuals studying dust-plasma interactions. Yet the sizes of the observed grains did not fully support this scenario. Many appeared too large to be influenced significantly by weak interplanetary magnetic fields. Even if some were susceptible, the uniformity of the tail's curvature required a level of coordination that natural magnetic environments rarely produce. In search of deeper clarity, researchers examined the relationship between the tail's shape and fluctuations in the solar wind. Patterns in the data revealed faint correspondences. At certain times, the tail curved inward more strongly during periods when solar wind density dropped. This inverse response did not match any established model. Instead of being pushed outward by reduced particle pressure, the tail seemed to settle into a shape that pulled toward the sun. It was as if the comet's dust cloud responded to the environment with its own internal logic, reacting to solar conditions in a manner that suggested hidden processes guiding its structure. During this period of investigation, ultraviolet imagery revealed another layer of complexity. Strands of the tail shimmered with faint emissions that hinted at high energy states in the dust particles. These emissions persisted even in regions of the tail where solar illumination waned. This persistence indicated that the dust might possess properties capable of storing and releasing energy in unexpected ways. The observations hinted at materials with characteristics rarely found in solar system objects, possibly shaped during the comet's journey through dense interstellar regions filled with energetic particles. Researchers analyzing the structural coherence of the tail also noticed faint wave patterns traveling through the dust cloud. These waves resembled oscillations moving slowly across the tail, with a rhythm distinct from any external forcing mechanism. Their presence introduced another dimension to the puzzle. If the tail's motion carried embedded oscillations, the shape might not be the result of environmental forces alone. Instead, the oscillations could originate from processes within the nucleus, or from interactions between dust grains and gases being emitted in highly coordinated patterns. In parallel deep space, antennas transmitting signals across the solar system detected small distortions when transmissions intersected the region near 3I Atlas. These distortions, subtle but measurable, suggested changes in plasma density that matched the unusual arcs of the dust tail. The plasma environment near the comet did not behave like the plasma surrounding other comets. Instead, it held faint structures that followed the contour of the tail. This correlation hinted that the dust might be interacting with plasma in ways unfamiliar to current science. Plasma physicists proposed that the comet could be producing its own boundary layer shaping dust and charged particles into an integrated system that responded to stimuli differently than isolated dust clouds. Meanwhile, visual observers on Earth continued to capture images that revealed increasingly strange behavior. At times, faint subtails formed branching gently off the main plume. These subtails did not align with sunlight or solar wind flow. Instead, they drifted along directions that matched neither gravitational predictions nor typical dust dynamics. Analysts studying the geometry of these branches noted that they appeared at intervals that echoed faint cycles observed earlier in the comet's brightness and coma structure. This connection suggested the possibility of internal rhythms that expressed themselves through every layer of the comet's environment. Another line of inquiry emerged when scientists considered whether the comet might possess a fragmented nucleus composed of multiple interacting regions. If the nucleus released dust in patterns shaped by internal structures, the dust streams might form arcs that behave unpredictably. However, high-resolution imagery from several orbiters showed no sign of fragmentation. The nucleus appeared intact, smooth and stable. The usual explanations involving rotating jets or irregular surfaces failed to account for the elegant curvature observed in the tail. A different approach examined the potential gravitational influence of unseen structures within the comet. If dense pockets of material existed below the surface, their gravitational pull might subtly direct the motion of dust grains. This idea required a nucleus with unusually high density variations. While such variations were not impossible, they seemed unlikely for a body exposed to billions of years of collisions in interstellar space. Most interstellar fragments lose internal complexity as they are eroded and fractured. Yet 3I Atlas appeared to retain subtle forces capable of guiding dust across large distances. During this time, a joint team working with data from multiple observatories attempted to map the tail's deviations in 3 dimensions. Their reconstruction revealed that the curvature was not uniform. Instead, it spiraled ever so slightly as it extended outward. This spiral was not chaotic. It carried a clear, gentle rotation that did not correspond to the nucleus's known rotational period. The discovery added an intriguing twist to the mystery. It suggested that the dust might be responding to a rotational frame not tied directly to the comet, but to an external or emergent condition in the surrounding space. Even more intriguingly, the spiral curvature aligned faintly with the strange disturbances detected earlier in the solar wind. The connection was imperfect but suggestive. If the comet influenced the solar wind, and if the solar wind influenced the dust tail, then the tail's shape might represent a physical map of the comet's interaction with its environment. But this interpretation raised a deeper question. Why would the comet's interaction with the solar wind produce structures that defied the normal direction of force? The object continued its journey indifferent to the clamour of hypotheses rising behind it. In the deep quiet of space, its dust tail continued to bend in ways that contradicted the simplest expectations of physics. The shape did not announce itself with drama. It revealed itself slowly through layers of data that accumulated night after night. With each new observation, the tail seemed to whisper that something beneath the surface of 3I Atlas shaped the object in ways not yet captured by human understanding. A comet defying the sun itself became a symbol of the deeper, more hidden processes waiting to be uncovered. The direction of the tail bending against logic stood as another piece of a growing puzzle. The solar system had never seen a visitor behave quite like this, and the mystery continued to deepen. Deep spectral shock. With every new observation, researchers hoped the spectral data might offer a stabilizing reference point, a domain where chemistry and physics could reassert their familiar order. Spectroscopy had long been the anchor of comet science, a method that peeled back layers of mystery by reducing light into measurable components. Yet when 3I Atlas revealed its spectral signature in full resolution, the anchor slipped. Instead of clarity, the outcome created the most profound disturbance yet. The spectral profile delivered a combination of signals no one had anticipated, signals that placed the comet outside the boundaries of established cometary chemistry. The first alert originated from a Hawaiian observatory. A researcher conducting routine line identification noticed something unsettling. Several absorption features appeared where the spectral template predicted emptiness. These features did not match any common volatile associated with comets, nor did they correlate with exotic compounds previously identified in rare interstellar clouds. They belonged to no catalogue used in solar system astronomy. At first, the team suspected calibration problems. Spectrographs can drift, sensors can fatigue, and faint targets can deceive even robust instruments. However, multiple recalibrations did nothing to reduce the signals. When the data held firm, the researcher contacted colleagues abroad. Within hours, observatories in Spain, Chile, and South Africa confirmed the same anomalous lines. These independent confirmations transformed suspicion into certainty. Something within the coma of 3I Atlas emitted patterns that did not fit familiar chemical frameworks. The newly observed lines hinted at molecules capable of surviving conditions that usually demolish fragile compounds. Their resilience suggested either a protective matrix within the dust, or an environment inside the nucleus that preserved them across unimaginable distances. Both interpretations carried implications that left the scientific community uneasy. The next surprise emerged when specialists examined the fine structure of several emission lines linked to ionized particles. Instead of the broad, energetic profiles typical of excited gas in cometary comas, the lines displayed narrow shapes indicating unusually stable excitation states. Such stability hinted at conditions far more controlled than those usually associated with chaotic sublimation. A group of atomic physicists gathered to evaluate the findings. Their analysis revealed that the ions appeared to occupy energy levels rarely seen in natural astrophysical environments. These levels suggested interactions involving fields or pressures not commonly found around objects with such low mass. Moving beyond the ionized components, researchers focused on the infrared region, hoping it would provide clues about deeper structures within the dust. Instead, the infrared spectrum introduced another layer of strangeness. Several vibrational modes appeared that resembled those of complex carbon networks, yet the patterns did not match any known structures, catalogued from meteorites, comet samples, or interstellar grains. These modes hinted at architectures that might have formed in extreme environments, perhaps near volatile rich star-forming regions, or near the remains of supernova activity. Whatever their origin, the carbon structures did not behave like typical organic compounds. They absorbed and re-emitted infrared radiation with a precision that defied usual thermal fluctuation. One of the most startling discoveries came from a high-resolution spectrograph in Chile capable of isolating isotopic ratios. Typical comets display isotope distributions that reflect the environment of the early solar system. Interstellar objects often show ratios shaped by foreign stellar processes, but 3I Atlas delivered ratios that match neither system. Instead, the distribution formed a pattern whose alignment with known cosmic signatures was only partial, as though the comet carried pieces of matter forged across multiple astrophysical regions. This pattern unsettled researchers. The distribution hinted at a history too complex for standard comet formation models. While teams analysed the chemical and physical composition, a separate clue emerged from the faintest regions of the spectrum. Deep scans in the far ultraviolet revealed weak signatures associated with molecules that normally dissociate within minutes under solar radiation. The molecules' presence implied that they must be forming continuously or receiving protection from some shielding mechanism. Observers suggested that the comet's coma might contain regions of lower radiation penetration than previously assumed. But mapping the coma's density revealed no obvious pockets dense enough to provide such shielding. The persistence of these fragile molecules remained one of the most perplexing aspects of the spectral data. New confusion followed when researchers examined the rotational lines associated with several gases. These lines displayed subtle asymmetry signs that the molecules experienced forces not accounted for by temperature or density gradients. The asymmetries implied that the gas might be interacting with fields or energy distributions emerging from the nucleus. Specialists in molecular dynamics examined the profiles and concluded that the patterns resembled conditions found in controlled laboratory environments where electromagnetic fields shape molecular behavior. Such conditions do not occur naturally around comets. Further investigation into the dust component revealed another layer of complexity. Different wavelengths suggested that dust grains possessed optical coatings that altered their reflectivity in ways not typical for natural dust. Some measurements hinted at surfaces structured at microscopic level structures that influence scattering in precise ways. These findings raised speculation that the grains might contain mineral phases shaped by intense heat or shock events, yet the same grains also contained volatile residues that should have evaporated under such conditions. The contradictory combination suggested a hybrid history that defied simple narrative. At the same time, mid-infrared observations detected faint signals resembling phonon modes associated with certain crystalline lattices. These lattices were unlike those found in terrestrial minerals or meteoritic samples. Their presence suggested that the comet might contain crystals grown under extremely slow or extremely fast cooling conditions, perhaps within nebular environments, with unusual pressure or composition. These materials, if confirmed, would place 3I Atlas in a category of its own, a relic shaped by environments not typically linked to cometary formation. Another striking discovery emerged when scientists examined temporal variations in the spectral data. Instead of remaining constant, several spectral features exhibited slow pulses rising and falling in intensity at intervals that did not match the comet's rotation or known environmental cycles. These pulses suggested that material within the coma might be released in periodic waves. The origin of these waves remained unclear. They could signal layered structures inside the nucleus, or they might reflect deeper processes occurring within the comet itself. Whatever their cause, the pulses expanded the sense that 3I Atlas operated according to internal processes not yet understood. In addition to these findings, astronomers using high-resolution spectrographs located on the Atacama Plateau identified faint absorption dips superimposed on emission lines. These dips hinted at intervening material positioned in front of the bright regions of the coma. If the material formed coherent structures, this raised the possibility that the coma possessed internal layers shaped by forces beyond thermal motion. Such layering would align with earlier observations of concentric ripples, although the connection remained speculative. As the spectral data accumulated, the overall picture became increasingly complex. The comet presented a blend of chemistry, physics, and energy distribution that resisted integration into familiar frameworks. The spectral signals pointed toward a body shaped by environments that no solar system object had experienced. Some aspects mirrored conditions found near young stars. Others aligned with processes seen in the remnants of dying stars. Still others held signatures that did not correspond clearly to any known cosmic region. Through all these revelations, one theme persisted. The surface and interior of 3I Atlas held secrets accumulated across a journey that spanned immense regions of the galaxy. The comet bore witness to physical conditions and chemical processes that rarely leave surviving traces. In its drifting glow, observers glimpsed echoes of places the solar system had never known. Spectroscopy usually transforms mystery into clarity. In this case, it exposed deeper layers of uncertainty. Each new line ratio and pulse added to a growing sense that the comet carried the imprint of a cosmic story far more elaborate than anticipated. What the spectrum revealed was not an answer, but a threshold. Beyond that threshold lay a world of processes waiting to be uncovered. The Mars Shadow event. As 3I Atlas continued down its enigmatic trajectory, one moment stood apart from all others in the minds of the researchers who followed its path. This moment arrived not in full sunlight, but in darkness. When the comet slipped behind Mars from Earth's perspective, scientists anticipated a predictable drop in brightness, a simple outcome governed by nothing more than geometry. Light from the sun would be blocked by the planet. The glow of the coma would fade. The tail would dim. It was a straightforward expectation, yet nothing about this object belonged to the straightforward. The instant 3I Atlas crossed into the planetary shadow, an unexpected radiance began to stir within the coma. Instead of dimming, the comet brightened. The glow rose slowly at first, then strengthened with a persistent, steady rise. Observatories across the world recorded the phenomenon in near disbelief. This was not an illusion caused by atmospheric distortion or instrumental error. Independent facilities operating at different latitudes and using different technologies captured the same luminous swell as Mars eclipsed the comet from sunlight. The event formed the first clear sign that 3I Atlas responded directly to darkness in a way that contradicted the behavior of natural cometary materials. Without sunlight, volatile compounds should have cooled, shrinking the coma and reducing emissions. Instead, the coma pulsed with light, a phenomenon that challenged every conventional model. Researchers attempted at once to quantify the rise. Photometric analyses showed that the brightness increased by a measurable percentage that varied depending on the wavelength observed. Shorter wavelengths brightened slightly more than longer ones, suggesting that the emission was not simple thermal glow. Something internal was awakening, ignoring the absence of sunlight. The behavior drew immediate scrutiny from specialists in plasma interactions. They considered whether the comet might have accumulated charge while in sunlight and then discharged it once in shadow. Such a process could theoretically create a temporary increase in glow, but this idea faltered when analysts examined the shape and duration of the brightness curve. The rise lacked the sharp profile associated with electrical discharges. Instead, it unfolded in a controlled, quiet ascent as if powered by a slow release of energy stored within the coma itself. As researchers examined the timing more closely, they discovered that the glow began exactly as the comet crossed the terminator, the boundary where Mars separated sunlight from shadow. The precision of this timing unsettled many. Natural processes rarely adhere to such exact thresholds. The glow intensified throughout the period of occultation and reached a plateau once the comet settled into the deepest portion of the shadow. This plateau persisted even as the comet drifted behind Mars's silhouette, hidden from both sun and Earth. In that darkness, it glimmered like a lantern lit beneath the planet's curved shadow. At the same time, orbiters circling Mars recorded data that suggested the event generated subtle but widespread disturbances in the surrounding environment. MAVEN detected small waves in the ionized particles trailing behind the comet. These waves appeared rhythmic, as though driven by pulses from within the nucleus or the coma. Instruments attuned to magnetic field behavior registered faint oscillations that did not correspond to any natural Martian processes. Although the disturbances were weak, their presence hinted that the brightness surge was not merely optical. It carried an imprint that reached into the surrounding plasma-shaping conditions in a measurable way. Meanwhile, spectrographs recorded alterations across several emission lines. During the shadow passage, certain lines intensified sharply, while others remained unchanged. Analysts found that molecules sensitive to low-energy excitation became far more active, as if stimulated by a mechanism unrelated to sunlight or temperature. The persistence of these emissions suggested that the comet might contain compounds capable of generating light through processes not governed solely by thermal dynamics. This possibility prompted considerations of energy storage mechanisms rarely applied to cometary materials. Some researchers wondered whether the comet's structure could contain layered materials capable of releasing energy in darkness. If some portion of the nucleus held metastable compounds, formed during its journey through interstellar space, exposure to shadow could trigger transitions that release photons. This idea required conditions rarely encountered in natural environments Yet the data encouraged consideration of possibilities beyond standard comet chemistry. As the occultation unfolded, a more subtle effect appeared. Observers noted faint arcs of diffuse light around the region where the comet lay hidden behind Mars. These arcs carried a softness reminiscent of auroral bands. They shimmered with low intensity, yet persisted long enough to be recorded by several ground-based and orbital instruments. Analysts proposed various explanations. One idea suggested that the comet's coma interacting with the thin Martian exosphere generated a faint halo through particle collisions. Another possibility considered whether the dust or gas released by the comet could scatter light refracted through Mars's atmosphere. Both ideas offered fragments of insight but failed to account for the arc's smooth curvature and unusual consistency. When the comet finally emerged from behind Mars's shadow, another unexpected moment occurred. Instead of returning gradually to baseline brightness, the coma dimmed with elegant symmetry, mirroring the rise that had taken place earlier. The brightness receded as though following a carefully scripted pattern, not a chaotic reaction to changing solar conditions. The tail also responded, shifting slightly as if adjusting to the new light environment. The transition lasted long enough for instruments to capture every step of its descent. By comparing the entry and exit curves, analysts discovered that both transitions followed nearly identical profiles. This mirrored behavior suggested that a single mechanism controlled the glow. The symmetry of the rise and fall strengthened the idea that internal processes within 3I Atlas governed the phenomenon. The comet appeared to respond to the absence and return of sunlight with precision, as if its materials possessed properties finely tuned to changes in illumination. As researchers examined the event from multiple angles, they noticed a final crucial detail. The brightness surge did not appear uniformly across all wavelengths. Instead, the increase showed a preference for lines associated with certain molecular species. This indicated that the glow was not purely structural but chemical in nature. Some molecules were activated in darkness, others were not. The pattern pointed toward a complex internal environment, where energy might transfer between different compounds through poorly understood processes. The Mars shadow event, as it came to be known, forced the scientific community to confront the possibility that 3I Atlas operated under conditions far removed from the predictable behavior of solar system comets. The surge of brightness in darkness, the symmetrical transitions, the plasma disturbances, the spectral irregularities, and the faint arcs around the shadowed region collectively suggested a deeper underlying mechanism connecting the nucleus, coma, and tail in ways not yet captured by existing theories. For researchers observing the event, the moment carried a quiet awe. In the darkness behind Mars, the comet had shown something unexpected and profound. It had revealed a core of behavior shaped not by the sun nor by gravity alone, but by a hidden rhythm that traveled with it across the galaxy. The shadow had not dimmed the object. Instead, it had illuminated the mystery at its heart, patterns in the noise. As 3I Atlas pushed farther along its curious path, researchers began sifting through a growing ocean of data collected from telescopes, satellites, and Martian orbiters. What initially seemed like scattered anomalies slowly began to reveal faint structure signals so subtle they hovered at the edge of detection. At first, these signals appeared random, dissolving into the ordinary turbulence of measurement errors and cosmic background fluctuations. But as more datasets accumulated and overlapped, a deeper coherence emerged. Within the noise patterns formed. The earliest hint of such structure appeared in a set of photometric readings taken from a high-altitude observatory in South America. The brightness variations recorded over multiple nights carried small modulations that did not correspond to any known periodic influence. They were not tied to the comet's rotation, nor to solar wind cycles, nor to changing perspectives from Earth. Instead, the modulations seemed to breathe, expanding and shrinking in a rhythm that resisted direct comparison with recognized astrophysical processes. When analysts stitched the readings together, they observed a faint rise and fall, occurring at intervals that defied simple categorization. Around the same time, a radio observatory in Australia detected fluctuations in signal strength when distant transmissions passed near the region of space occupied by 3I Atlas. These fluctuations were not dramatic yet, they repeated often enough to draw attention. When plotted, they formed clusters concentrated along narrow bands of phase delay. The clusters gave the impression of invisible structures embedded in the space surrounding the comet, structures that altered radio waves just enough to leave a signature. What generated these structures remained unclear. but the consistency of the effect suggested that the space around 3I Atlas was not as uniform as expected. Meanwhile, spectroscopic measurements showed slight shifts in the intensity of several emissions occurring at unpredictable intervals. These shifts rose and fell as though responding to mild pulses within the coma. The origin of these pulses remained hidden. They did not track any known cycle of illumination. They did not correlate with the tail's peculiar curvature. Instead, they appeared to follow an inner cadence that had yet to be traced to a physical cause. Specialists studying the signals remarked that the data carried a sense of organized repetition, albeit one too faint to decode. Another set of observations gathered from multiple telescopes during a coordinated campaign revealed changes in scattered light from the dust cloud. These changes formed geometric motifs that appeared only when a specific angle between Earth, Sun, and Comet occurred. The motifs resembled faint arcs, or bands barely distinguishable from background contamination. Yet the arcs returned during every observation run where the geometry matched. Their presence pointed toward dust distributions shaped by more than random collisions or solar forces. Whatever created the arcs did so consistently, leaving trace signatures in the reflected light. As the list of subtle irregularities grew longer, a multidisciplinary team attempted to overlay datasets from different wavelengths. When this cross-comparison was performed, a new pattern emerged. Several independent anomalies aligned with one another in time despite being recorded through unrelated instruments. For instance, slight distortions in radio transmissions coincided with shifts in ultraviolet emission strength. Variations in dust scattering matched changes in faint plasma concentrations recorded by orbiters trailing behind Mars. The coincidence was too persistent to dismiss. Analysts noted that the timing overlap hinted at a single underlying source influencing multiple layers of the comet's behavior. To further investigate, computational specialists applied algorithms designed to detect hidden periodicities. These algorithms filtered out random variations, isolating the moments when signals converged across instruments. The results highlighted recurring nodes in time where the comet's environment appeared to undergo coordinated changes. The nodes were subtle but persistent. They suggested that 3I Atlas possessed internal processes capable of shaping the coma dust and surrounding plasma all at once. Yet no known natural mechanism acted across so many physical domains with such gentle coherence. Intrigued researchers focused on precisely when these nodes occurred. The timing revealed an unusual feature. The nodes clustered around points where the comet crossed regions of space with slightly altered solar wind characteristics. The connection was not straightforward. The solar wind varied often and unpredictably, and the changes observed here were too mild to cause major cometary reactions. Yet each time the comet passed through certain narrow corridors of particle density, the subtle patterns intensified. This observation suggested that the comet might be responding to small variations in the interplanetary environment, with sensitivity far greater than normal. To probe this possibility, teams examined whether the comet's surface might contain materials capable of rapid energy exchange at low thresholds. Some minerals and carbon structures can absorb energy from charged particles and release it later in controlled bursts. If 3I Atlas carried such materials, they might generate faint pulses detectable across multiple wavelengths. However, the available spectral data offered no clear confirmation. While hints of exotic compositions existed, the evidence remained too fragmented to support a definitive conclusion. Another idea arose from the behavior of the dust tail. Analysts monitoring the tail's unusual curvature noticed tiny adjustments occurring during the same intervals identified as nodes in the data. These adjustments formed micro-arcs that shifted in tandem with changes in plasma behavior near the comet. If the dust responded to these changes, it would imply that the environment around the comet oscillated in a manner that influenced both dust motion and energy emissions. This possibility added another layer to the growing complexity of the phenomenon. As researchers continued to analyze the nodes, they discovered something more enigmatic. A number of faint correlations linked the nodes not only to external conditions, but also to internal structural cues. For example, slight changes in the emission of certain molecular lines corresponded closely with variations in brightness pulses observed during earlier sections of the comet's journey. The alignment was subtle but consistent enough to suggest that some internal feature of the nucleus might be guiding the timing. If the nucleus possessed layered regions that released energy or dust in cycles, these cycles could imprint upon the cloud surrounding the comet. Curiously, the patterns appearing in the data did not behave like the signals of rotational dynamics. They lacked the regularity expected from a spinning body. Instead, the cycles seemed to drift as though shaped by processes sensitive to external conditions yet rooted in internal structure. Analysts likened the behavior to a natural oscillator reacting to environmental input. The metaphor captured the sense that 3i Atlas functioned less like a passive body and more like a system responding dynamically to its surroundings. As more time passed, researchers began to consider whether the comet carried within it a network of fractures or cavities that allowed gases or particles to resonate under specific conditions. If the interior structure behaved like a vast irregular instrument, shifting pressures could create subtle oscillations that propagated outward into the coma. These oscillations might interact with dust and plasma to create detectable patterns, yet such a system had never been documented in a natural object. The idea remained speculative, but the behavior of 3i Atlas encouraged the exploration of possibilities not typically considered in comet science. The most compelling realization emerged when all available datasets were plotted simultaneously. The combined view revealed a pattern that resembled a shifting mosaic, each fragment of data aligned with others at specific intervals, forming a momentary unity before dissolving into noise again. This mosaic did not point toward a single explanation. Instead, it implied the presence of underlying processes too faint to isolate directly, yet strong enough to shape multiple domains at once. The patterns hidden within the noise formed a quiet indication that the comet possessed a depth of behavior seldom seen in natural bodies. Its interior surface coma and surrounding space appeared linked in ways that exceeded the boundaries of ordinary dynamics. With every new discovery, the idea grew clearer. 3i Atlas did not merely carry a mystery. It generated weaving signals into the fabric of the solar system that hinted at a richness of processes waiting just beyond comprehension, a map of distortions. As researchers pushed further into the data surrounding 3i Atlas, a new category of irregularities began to emerge, one that did not belong to chemistry brightness or plasma alone. It manifested instead in the delicate measurements of position motion and the pathways of signals passing near the comet. Astronomers had long trusted astrometry to reveal the subtle gravitational influences acting on celestial bodies. Tiny shifts in position could uncover unseen forces companions or structural mass differences. Yet the shifts appearing around 3i Atlas formed no ordinary gravitational story. They formed a pattern of distortions that stretched across space like faint scars on an invisible surface. The first sign of these distortions arrived from a team working with long baseline interferometry. Their method combined signals from observatories separated by thousands of kilometers, allowing them to measure minute angular displacements with exceptional precision. During several observation windows, they noticed that the comet's position drifted by amounts too small to disrupt overall trajectory but too structured to dismiss. These drifts appeared as tiny bends in the computed light paths, as though the photons passing near the comet encountered slight irregularities before reaching the instruments. The effect was not strong enough to imply gravitational lensing. Instead, it resembled the gentle warping of space that occurs when charged plasma interacts with electromagnetic waves. In an attempt to confirm the anomalies, the team coordinated with radio telescopes tracking distant pulsars. Pulsar signals provide some of the most stable timing references in astronomy, and any deviation in their arrival times often betrays changes in the space they traverse. When analysts examined pulsar data collected during intervals, when the signals grazed the region around 3i Atlas, they found minute delays and advances. These timing offsets were not random. They appeared in clusters forming sequences that loosely mirrored variations in plasma density recorded earlier by spacecraft. The alignment between the timing shifts and the plasma fluctuations hinted that space near the comet harbored irregularities capable of altering the passage of electromagnetic waves. Meanwhile, optical instruments measuring background stars noticed slight distortions in their positions when 3i Atlas passed nearby. These distortions did not match gravitational predictions. Instead, the star's apparent positions wavered in patterns that suggested refractive influences. Such refractive effects can occur when light passes through uneven distributions of dust or gas. However, in this case, the distortions extended far beyond the boundaries of the visible coma. This widespread reach implied that something subtler than dust or gas shaped the region. Analysts studying the phenomenon remarked that the distortions resembled the effects seen in regions of fluctuating plasma, yet the shape and timing of the distortions did not fully align with typical plasma refractive behavior. A further clue emerged when scientists examined how signals from spacecraft moved through the region near the comet. Several transmissions experienced tiny but persistent polarization shifts. These shifts varied in ways that suggested the presence of an anisotropic medium, a medium whose properties differed depending on direction. The discovery sparked intense discussion among specialists. If the space around the comet behaved like an anisotropic environment, it could indicate that charged particles or magnetic structures formed temporary filaments that altered the propagation of electromagnetic waves. Such filaments have been observed in the solar wind, but never in association with a comet in such a structured form. These observations became even more intriguing when nights of exceptional visibility revealed faint irregular halos around distant stars viewed through regions adjacent to the comet. The halos appeared only under certain angles and dissolved quickly as the comet advanced. Their fleeting nature made them challenging to capture, yet multiple observatories managed to record them. When analysed, the halos displayed asymmetric forms that could not be explained by atmospheric interference. Instead, the shapes suggested that light passing through the region encountered patches of refractive material arranged in irregular patterns. These patches might be linked to the dust and plasma anomalies observed earlier, but their structure implied a coherence that natural turbulence seldom produces. Researchers attempted to map the distortions by overlaying all available datasets. The result revealed a faint but persistent topology surrounding the comet. This topology resembled a shifting shell, composed of regions with varying refractive or plasma density characteristics. The shell did not remain static. It pulsed, expanded and contracted, though not exactly in sync with the brightness cycles noted in other observations. Instead, it followed its own cadence, one that seemed loosely tied to the faint intervals identified earlier in the comet's multi-wavelength data. The cadence created the impression that the comet carried an internal rhythm capable of influencing its surroundings. Some theorists considered whether the distortions might originate from interactions between the comet's material and the solar wind's interplanetary magnetic field. If certain regions of the comet released ions in patterns that aligned with magnetic flux lines, they might create temporary structures capable of bending or delaying light. This idea found partial support in data showing that distortions were strongest when the comet crossed regions where the magnetic field lines formed gentle curves. However, the strength and coherence of the distortions still exceeded what could be easily explained through such interactions. Another concept explored whether the comet's nucleus possessed properties that allowed it to generate weak fields of its own. Certain exotic materials shaped under extreme astrophysical conditions could theoretically retain magnetic or electric characteristics for long periods. If the nucleus harbored regions that released charge in controlled ways, it might create temporary boundaries in the surrounding space. These boundaries, though faint, could influence the pathways of passing photons. The idea lacked concrete empirical grounding, but it aligned with a number of scattered clues present in the comet's behavior. As more data arrived, researchers noticed that the distortions tended to intensify during periods of reduced solar wind turbulence. This counterintuitive behavior intrigued specialists. Usually calmer solar conditions reduce irregularities in space. In the case of 3I Atlas, the opposite occurred. The distortions sharpened during quiet periods as though the comet's influence became more pronounced when external noise diminished. This finding suggested that the comet's internal or local processes might operate independently of the larger heliospheric environment, responding to its own dynamics rather than the sun's fluctuations. In a parallel effort, computational astrophysicists attempted to represent the region around the comet, using models adapted from plasma boundary simulations. Although the models successfully reproduced some aspects of the distortions, they failed to match the full complexity seen in the observations. The simulations lacked the layered structure evident in the real data, particularly the subtle pulses that moved through the region. This discrepancy implied that the comet interacted with space in a more intricate way than existing theoretical tools could easily reproduce. As the mosaic of distortions grew clearer, a subtle realization took hold among the teams analyzing the phenomenon. The region around 3I Atlas did not behave like passive space. It behaved like space undergoing constant delicate rearrangement. The comet appeared to carry an internal architecture capable of creating ripples in its surroundings, ripples that altered how light and signals traveled through the area. These ripples were not dramatic enough to imply extreme forces, but persistent enough to reveal a consistent guiding influence. The emerging map of distortions offered a new layer of insight into the enigma that was 3I Atlas. Every distortion, every delay, every refracted line hinted at processes operating beneath the surface, shaping the space around the comet, with a sophistication unlike anything observed in natural bodies. Whatever forces sculpted the comet's behavior extended outward, touching the vacuum itself with patterns waiting to be deciphered. The turning point. As observations mounted and the archives of data swelled, researchers began sensing a quiet shift taking place beneath the surface of their analyses. For weeks, the investigation had followed a familiar rhythm. Irregularity appeared, explanation failed, new theories emerged, and more observations complicated the picture. But somewhere along this expanding timeline, an inflection point arrived. It emerged not in a single dramatic event, but in the convergence of countless subtle clues that made one truth increasingly unavoidable. The anomaly surrounding 3I Atlas no longer resembled an unusual comet. It had begun to resemble a system operating on principles scarcely touched by existing frameworks. The first hint of this turning point came when a research consortium assembled a combined dataset, integrating position shifts, spectral variations, brightness cycles, plasma turbulence, and tail morphology. The integration revealed patterns that had eluded detection when the data was examined separately. A faint synchrony appeared, linking phenomena that at first seemed unrelated. Slight fluctuations in certain emission lines aligned with tiny changes in dust acceleration. Subtle distortions in the surrounding space coincided with quiet pulses in the coma. These correspondences were weak, but their persistence suggested that the comet's visible behavior might be driven by a hidden internal structure. As analysts studied these correlations, they noticed that some intervals of heightened activity occurred during moments when the comet crossed regions of low particle density in the solar wind. Under such conditions, comets typically become less active. Yet 3I Atlas showed nuanced enhancements in several metrics precisely when environmental forces diminished. The alignment did not indicate chaos. Instead, it hinted at a response that followed an internal logic, as if the comet adjusted its behavior when external interference decreased, revealing its underlying processes more clearly. In parallel, a team focusing on the comet's infrared emissions made a discovery that altered the direction of the investigation. When they filtered out background signals and examined only the emission levels associated with structural compounds in the dust, they found subtle periodic shifts. These shifts suggested that certain materials within the coma underwent transitions between states in a rhythm not tied to solar illumination or rotation. It appeared as though molecules deep within the dust cloud oscillated between different energy levels in a coordinated fashion. Such coordination implied interactions occurring on scales too fine to be governed by simple sublimation. The infrared findings prompted researchers to revisit the earlier chemical anomalies identified in the spectral analyses. When they overlaid the timing of molecular transitions with data from plasma fluctuations, they found a faint but consistent pattern. The comet released charged particles in minute bursts that loosely mirrored the molecular rhythms identified earlier. These bursts were not strong enough to shape the comet's trajectory in any substantial way, yet they appeared synchronized enough to raise questions about the internal structure of the nucleus. If the nucleus possessed regions that trapped and released energy in cycles, these cycles might ripple outward, influencing dust and plasma alike. In another corner of the analysis, dynamicists studying the comet's acceleration curve discovered that the rate of unexplained thrust increased slightly during intervals when the internal rhythms were most pronounced. This discovery further deepened the mystery. The acceleration remained too smooth to originate from random jets, yet too weak to indicate any deliberate propulsion mechanism. The interplay between acceleration and internal rhythms reinforced the notion that the comet's motion responded to energy exchanges occurring within its structure. As these insights accumulated, certain long-standing assumptions began to lose their strength. For months, researchers had tried to fit the comet's behavior into categories shaped by prior knowledge of interstellar bodies, but the closer they looked, the less those categories held. Typical comet models assume sublimation-driven jets, chaotic dust motion, and sporadic emission bursts shaped by surface irregularities. 3I Atlas refused each of these assumptions. Its coma expanded with an unusual symmetry. Its dust tail curved in defiance of the sun. Its spectral lines revealed compounds arranged in patterns that hinted at long histories through extreme environments. Its plasma environment shifted with a quiet coordination unlike normal turbulence, and its path through space twisted with a consistency that hinted at underlying processes not yet named. Faced with these contradictions, a growing number of teams shifted toward more flexible approaches. Instead of forcing the observations into familiar structures, they began exploring frameworks that accommodated complex interconnected systems. Some explored whether the comet could contain internal cavities linked by networks of microchannels that distribute heat or pressure in coordinated patterns. Such an arrangement, while rare in nature, might allow the comet to respond to environmental changes with subtle, internally driven adjustments. Others considered whether slow-moving lattice structures within the nucleus might shift in response to magnetic or gravitational gradients, releasing dust or ions in patterns complex enough to influence observable behavior. Another contingent examined the possibility that 3I Atlas passed through astrophysical regions that shaped its internal structures in ways seldom seen in the solar system. For example, the comet might have drifted through regions rich in exotic molecules that stabilized within its interior in unusual forms, or it might have encountered shock waves from distant stellar events that restructured its materials. These scenarios imagined the comet not as a relic of a single environment, but as a record of multiple cosmic encounters. The most intriguing interpretation arose from those studying the comet's faint internal rhythms. These rhythms, appearing across spectral lines, plasma fluctuations, and dust behavior, hinted at an internal feedback process. If the comet possessed layered regions that responded to pressure, temperature, or radiation, by cycling energy inward and outward, these cycles might manifest as coordinated pulses. Such feedback processes could theoretically explain the gentle accelerations, the synchronized distortions, and the periodic changes in emission signatures. Although speculative, the concept offered a cohesive way to understand the multiple linked anomalies. Even more intriguing was the possibility that the rhythms resulted from interactions between the comet's internal materials and its external environment. Under this interpretation, 3I Atlas behaved almost like a natural resonator responding to solar conditions with structural vibrations or energy exchanges that influenced its surroundings. If such resonances existed, they would mark the comet as a body capable of storing and releasing energy across scales far subtler than any seen in typical comets. Through all these developments, a subtle shift occurred in the scientific community's tone. What had begun as an investigation into an unusual visitor slowly transformed into a study of an entirely new category of interstellar phenomenon. The deeper researchers probed, the more they sensed that 3I Atlas contained features shaped by processes not commonly encountered in comet science. Each layer of data revealed another layer beneath it, suggesting that the comet was less a simple chunk of ice and dust, and more a complex structure assembled across cosmic epochs. This realization marked the turning point. It no longer mattered whether the anomalies could be explained by expanding knowledge, or whether they pointed to a new type of astrophysical system. What mattered was that 3I Atlas demanded a rethinking of how interstellar objects are understood. The comet did not break physical laws, it expanded the space where those laws operated, and in doing so it transformed itself from a curiosity into a threshold object, a marker standing between the known and the not yet comprehended. By the time researchers recognized the full significance of this shift, 3I Atlas had already moved deeper into the inner solar system. Ahead of it lay regions bathed in stronger sunlight, places where further mysteries would unfold. For those tracking its path, the turning point offered neither answers nor closure. It offered perspective. The comet had revealed enough to show that the story was far larger than anticipated, and the next stages of its journey promised to reveal far more. The unexpected resonance. As 3I Atlas approached a region of space where the solar wind thinned into a calmer stream, an unfamiliar signature began to form within the data. The signal did not resemble the rhythmic brightness pulses observed earlier, nor did it match the subtle timing nodes that had threaded themselves through the comet's behavior like a hidden metronome. This new phenomenon emerged in a quieter register, appearing first as minor fluctuations barely distinguishable from background static, yet once detected it grew steadily clearer. Something within the comet's environment had begun to resonate. The earliest indication of this resonance appeared in magnetometer data, transmitted by the orbital probes monitoring charged particle behavior ahead of the comet. During several observational windows, instruments recorded tiny oscillatory variations in the ambient magnetic field. These oscillations possessed a frequency too low to be linked to standard solar wind interactions. They drifted in and out of range, forming soft patterns that rose and fell in graceful arcs. When plotted, the oscillations formed sequences that hinted at a coordinated influence shaping the space around the comet. Nearly simultaneously, ground-based radio arrays detected faint modulations affecting long-distance signals. These modulations were gentle and narrow, noticeable only after extensive filtering. Their timing loosely paralleled the magnetic oscillations recorded by orbital probes. The parallel suggested a unity of cause, as though the signals and fields were responding to the same influence. The correlation intrigued analysts because it bridged two distinct observational domains. If the resonance influenced both charged particle behavior and radio transmissions, then it operated across multiple physical pathways. Alongside these observations, ultraviolet instruments monitoring the coma identified minor alterations in the emission strength of several molecular lines. The lines dimmed and brightened with a faint rhythm that aligned imperfectly with the oscillations but remained too consistent to be dismissed. Such alignment hinted that the resonance touched not only electromagnetic processes, but also molecular activity within the coma. The phenomenon appeared to ripple across different layers of the comet's environment, suggesting a unifying mechanism operating beneath the surface. In another corner of space, an array of deep space antennas tracking the comet's position noticed that the curvature of certain refractive distortions shifted during the resonance intervals. These shifts did not imply dramatic changes in the comet's surroundings. Instead, they appeared as subtle adjustments in the shape of the distortions, as if the ripples in the surrounding space had momentarily sharpened. The adjustments vanished as quickly as they appeared, returning the region to its earlier structure. The temporary change suggested that the resonance altered the configuration of the plasma filaments around the comet just enough to be detected. Eager to understand the scope of the phenomenon, researchers focused on the timing of the resonance itself. The oscillations intensified as the comet entered a zone where the solar wind's density dipped to unusually low levels. The reduced particle pressure created an environment with fewer external disturbances, a vacuum in which minor processes could rise into visibility. In this quieter space, the resonance settled into a more stable rhythm. Instruments monitoring the comet found that the oscillations repeated with increasing clarity, forming a pattern that spanned multiple wavelengths and particle behaviors. The pattern did not conform to simple periodicity. Instead, it expanded and contracted in cycles that carried a fainter symmetry, as though shaped by a process that evolved over time rather than repeating perfectly. The asymmetry added an elusive quality to the resonance, giving it a living cadence rather than a mechanical one. For those analyzing the data, the resonance felt less like an imposed structure and more like a soft internal pulse, interacting with its environment in a way that responded to external conditions. As the resonance grew clearer, researchers began examining whether the nucleus itself might serve as the source. The idea gained momentum when thermal instruments detected tiny, synchronized shifts in temperature distribution along the nucleus's surface. The temperature changes were delicate, too small to indicate large-scale activity such as geysers or outbursts. Instead, they followed gentle gradients that matched the timing of the resonance cycles. These gradients suggested that heat was being redistributed across the nucleus in a coordinated manner. The possibility of internal conduits or layered materials capable of channeling energy became increasingly plausible. This line of thinking gained further support when dust monitoring instruments recorded small shifts in the velocity distribution of particles released from the nucleus. During resonance periods, dust grains gained or lost minute increments of speed. The changes were subtle but consistent, implying that the release of dust responded to the resonance in ways not seen during ordinary comet activity. If the interior harbored structures that channeled energy outward, the resonance might shape how material left the nucleus, influencing everything from dust motion to plasma interaction. Another compelling observation emerged from spectrometric analysis. During resonance intervals, the intensity ratios between particular molecular emissions shifted slightly. These shifts indicated that energy was being redistributed within the coma in a structured way. The behavior resembled conditions found in controlled laboratory environments, where materials experienced gentle external fields. Yet in this case, no external field of the necessary type existed. The resonance offered the most coherent explanation. It appeared to guide or influence molecular energy states, imposing a subtle order upon the surrounding gases. One unexpected clue arrived from a study comparing the resonance's timing with the comet's acceleration regularities. Though the alignment was not exact, small accelerations appeared more often during intervals when the resonance strengthened. This correlation hinted at a deep link between internal energy processes and the comet's motion through space. If the resonance altered how energy moved within the nucleus, and if some of that energy escaped as jets too fine to be resolved, it might create small thrusts that guided the comet's trajectory. As data accumulated, modelers attempted to simulate the resonance using frameworks adapted from geophysical wave theory and plasma oscillation physics. The simulations captured fragments of the behavior, but left significant portions unexplained. The resonance refused to compress into a simple mathematical form. Each model that attempted to confine it revealed new layers of complexity, suggesting that the comet did not host a single oscillating process, but rather a network of linked processes interacting across different physical domains. In the background of these efforts, a broader idea slowly took shape. The resonance seemed to function like a structural heartbeat, not in the biological sense, but as a long-scale energy rhythm arising from the comet's internal composition. If the nucleus contained regions capable of storing and releasing energy gradually, the resonance might be the outward expression of those internal transitions. Such transitions could arise from interactions between layered materials exposed to cosmic conditions across immense spans of time. As the comet drifted through the quiet region of reduced solar wind activity, the resonance reached its most pronounced clarity. For several hours, the pulse threaded itself through every available data set. Dust velocity changes aligned with thermal gradients. Plasma oscillations matched molecular fluctuations. The distortions in surrounding space showed brief coherence. The sequence formed a moment where the comet's internal and external behaviors aligned into a unified pattern. That moment marked the first instance where observers felt they were glimpsing the deeper architecture of 3I Atlas. The resonance did not reveal the comet's secrets. It revealed that the comet possessed secrets structured enough to create a moment of harmony across multiple layers of observation. In that harmony lay the clearest indication yet that the object carried not chaos but order. An order faint, ancient, and woven into the very matter that composed it, the surface that refused to behave. As telescopes sharpened their focus on the nucleus of 3I Atlas, researchers expected the same rough fractured landscape seen on every comet ever studied. Ice exposed to sunlight should have cracked and spooled. Dust layers should have shifted with each thermal cycle. Micropores should have opened as volatile pockets escaped. Instead, the surface of 3I Atlas revealed a tableau that confounded even the most flexible expectations. It behaved neither like frozen rock nor like fragile organic dust. The nucleus possessed a quiet stability at odds with the stresses imposed upon it. The most detailed early images came from an observatory in the southern hemisphere, equipped with adaptive optics tuned for faint targets. When the team enhanced the raw frames, the surface appeared almost polished in places, as though resistant to the microfractures that characterize cometary evolution. Smooth regions alternated with clusters of geometric textures, each arranged in patterns that avoided the chaotic randomness usually seen in solar system comets. The geometry was not precise enough to suggest intentional arrangement, yet far too organized to be easily dismissed as coincidence. As higher resolution instruments weighed in, they revealed another peculiarity. Across several regions of the nucleus, faint variations in reflectivity followed curved paths that traced elegant arcs over the surface. These arcs aligned neither with topographical features nor with illumination angles. Their presence hinted that the surface materials responded to sunlight or thermal changes in a manner shaped by internal structure, rather than external erosion. Some analysts suspected that layers beneath the surface might expand or contract with modest fluctuations in temperature, creating patterns visible only at certain wavelengths. Building on these observations, researchers began comparing heat maps of the nucleus taken at intervals of several hours. These maps revealed thermal gradients that shifted with unexpected fluidity. Instead of remaining stable or following the familiar pattern of heating on the sunlit side and cooling on the shadowed side, the gradients expanded across the surface with gentle transitions that did not match the direction of solar illumination. The distribution suggested that heat was traveling through the nucleus along pathways that did not correspond to its apparent shape. Such behavior implied the existence of internal channels or materials capable of redistributing thermal energy with unusual efficiency. The stability of the surface became even more striking during a period when the comet experienced a minor increase in solar radiation. Comets typically respond to such increases with jets erupting from subsurface layers. These jets launch dust and gas into space, reshaping the landscape in abrupt and messy ways. Yet during the peak of illumination, 3I Atlas remained composed. A few faint wisps drifted from isolated points, but no large jets appeared. Instead, the surface continued its measured evolution, redirecting excess energy gently rather than explosively. This quiet resistance fueled speculation that the nucleus might possess physical properties, granting it greater structural cohesion than typical cometary materials. Support for this notion emerged when radar instruments studying surface roughness recorded signals that suggested a density profile inconsistent with porous ice. The signals reflected from deeper layers indicated that the subsurface possessed a strength and coherence unusual for bodies exposed to long-term interstellar erosion. If the interior contained materials that compacted under repeated cycles of pressure and temperature, they might form layers capable of channeling energy or resisting fractures. The radar returns hinted at the presence of strata that absorbed impacts and stress more effectively than the fragile interiors of solar system comets. As the investigation expanded, researchers observed that the surface hosted faint migrating streaks, visible only during specific phases of illumination. These streaks drifted over the nucleus at an imperceptibly slow pace, shifting position over the course of days. Their motion did not appear linked to rotation or sublimation. Instead, they resembled surface-level responses to internal adjustments, suggesting that underlying materials produce subtle movements detectable in the outer coatings. Such movements hinted that the nucleus might operate as a layered composite rather than a simple mix of ice and dust. Further anomalies appeared when scientists analyzed polarization data from reflected light. The light scattering patterns did not match the typical signatures expected from irregular porous surfaces. Instead, the polarization map suggested that some regions of the nucleus were composed of particles arranged with a degree of alignment, as if shaped by forces acting uniformly across broad areas. The alignment could not be explained by sunlight or rotation alone. Speculative models imagined that the comet's long journey through environments rich in magnetic or charged particle fields might have imprinted structural tendencies on the surface. These tendencies may have persisted, surviving billions of years of cosmic travel, while polarization studies unfolded. A separate team, examining spectral data from the surface, detected faint emissions that suggested the presence of embedded materials capable of altering light in specific ways. These emissions appeared strongest in areas where the geometric textures were most prominent. The spectral lines indicated compounds that reacted to low-intensity illumination, with near-instantaneous changes in reflectivity, as though responding to the environment with remarkable sensitivity. If such materials permeated the outer layers, they might form a dynamic skin capable of adjusting to external conditions, modulating how heat, light, and particles interacted with the surface. Among the most intriguing findings was the discovery of small regions that darkened and brightened with no connection to rotation or solar angle. These regions behaved like windows, revealing changes occurring beneath the surface. Their variations suggested internal redistribution of energy or material visible only in these localized patches. If the nucleus hosted pockets of material that gradually transitioned between different physical states, such transitions might manifest as subtle surface shifts detectable across multiple wavelengths. Yet the most significant clue arrived from the interaction between the surface and the dust surrounding it. Dust ejected from the nucleus often follows messy trajectories shaped by jets or surface irregularities. In contrast, the dust emerging from 3I Atlas adhered to narrow corridors that traced pathways linked to specific features on the surface. These pathways suggested a controlled release process shaped by underlying structures guiding the flow of dust into space. Such guidance implied an internal architecture capable of channeling material outward in intricately regulated patterns. As analysts reflected on the expanding portfolio of anomalies, a unifying insight took shape. The surface of 3I Atlas did not behave like the crust of a simple icy body. It behaved like the uppermost layer of a complex interior, a layer responsive to subtle forces and capable of reorganizing itself without fracturing. Its patterns, gradients and migrations hinted at internal processes unfolding with deliberate steadiness, shaped by environmental cues but governed by deeper structural logic. The nucleus seemed to contain a quiet intelligence built from physics rather than intention, an interplay of materials and energies arranged across cosmic timescales. Its surface acted as a membrane through which internal rhythms expressed themselves, reflecting deep emotions occurring far from view. For the researchers observing from afar, the surface offered a glimpse of a hidden architecture that stretched inward, suggesting that the mystery of 3I Atlas extended far deeper than previously imagined. The whispering interior. As the world's observatories continued their unbroken watch over 3I Atlas, attention gradually shifted inward. Every external measurement hinted at an interior that refused to behave like the core of a conventional comet. The absence of violent jets, the quiet redistribution of heat, the drifting patterns across the surface, the resonance that pulsed through dust and plasma, and the coherent distortions in nearby space all pointed toward processes unfolding beneath the outer shell. It became clear that the nucleus harbored a structure far more intricate than a frozen mass of ice and ancient dust. Something inside the comet moved rearranged or released energy with a steadiness that suggested an internal landscape governed by complex interactions. The earliest clues to this hidden world came not from imaging but from seismic-like signatures embedded in the light curves. Although comets do not produce classical seismic waves, variations in reflected light sometimes reveal vibrations within their cores. For 3I Atlas, a sequence of such variations began appearing in photometric data collected from multiple observatories. These variations were faint but repeated with patterns too deliberate to be written off as random noise. When aligned, they formed soft pulses that propagated through the surface layers at intervals that implied subtle, internal shifts. These pulses did not resemble the abrupt tremors produced by collapsing cavities. Instead, they rolled through the nucleus with gentle consistency as though shaped by a slow internal rhythm. Additional insight arrived when radar reflections revealed curious gradients in subsurface density. Unlike typical comets whose cores often contain porous interiors riddled with voids, 3I Atlas displayed alternating pockets of material with distinct density levels. These pockets arranged themselves in curved layers rather than chaotic clusters. The order suggested that the materials had settled or restructured themselves over vast spans of time, forming stratified domains, capable of channeling energy or pressure through the interior. The radar maps revealed transitions between layers that resembled gradual shifts rather than sudden fractures, hinting that the interior had evolved in a controlled manner. Such transitions gained significance when researchers compared radar data with thermal images. They found that heat coursed through specific layers with surprising efficiency. Instead of diffusing outward in an irregular pattern, thermal energy travelled along routes that followed the density gradients revealed by radar models. This behaviour resembled the flow of heat along mineral veins or crystalline lattices. It suggested that the interior hosted materials capable of conducting energy preferentially along certain paths. If true, these pathways might allow the nucleus to channel heat into pockets that store and release energy, slowly shaping the cycles observed at the surface and within the coma. Further evidence of interior dynamics emerged when dust released from the surface displayed velocity signatures that varied depending on the region of origin. Dust grains launched from certain points travelled slightly faster or slower than expected, as though guided by internal pressure pockets that varied across the nucleus. In some regions, dust escaped with soft acceleration that seemed tied to the deeper layers beneath the surface. In others, dust drifted outward with barely any momentum at all, implying regions where internal processes temporarily stabilized. Such differences challenged the assumption that sublimation alone propelled the dust. If interior structures governed how dust escaped, then the nucleus acted as a coordinated system rather than a chaotic one. A turning point in the study of the interior came when scientists examining polarization data noticed subtle periodic shifts in the polarization angle of reflected light. These shifts occurred even when the surface remained visibly unchanged, suggesting that something inside the comet momentarily altered the alignment of particles along the crust. Such alterations could arise if internal regions expanded, contracted, or rotated slightly relative to surrounding layers. The phenomenon resembled the behavior of materials under varying internal stress. The comet appeared to breathe its core shifting minutely in ways that affected the organization of surface particles. The idea of internal stress cycles gained further traction when spectroscopic analysis uncovered repeating fluctuations in emissions linked to specific molecular groups. These fluctuations were too smooth to suggest localized activity, and too synchronized across the coma to arise from separate regions acting independently. Instead, the pattern implied that the interior influenced chemical activity throughout the surrounding environment. If materials within the core underwent slow transitions between different states, or if energy moved between layers, the resulting shifts could create subtle chemical waves detectable from afar. While the chemical and photometric clues painted one part of the picture, plasma measurements painted another. Instruments detecting the charged environment around the comet noticed periodic changes in the behavior of ions released from the nucleus. These ions did not drift outward at constant rates, but instead accelerated or decelerated in small pulses that mirrored interior signals detected through other channels. The alignment implied that the comet released charged material in cycles dictated not solely by sunlight, but by internal processes unfolding in the shadows beneath the crust. In response to these findings, theorists began exploring models in which internal materials interacted with external forces in unexpected ways. One model envisioned the nucleus as a layered aggregate, where certain regions responded to temperature changes by shifting structure at microscopic scales. These structural shifts might create faint mechanical waves propagating through the interior, influencing dust-release plasma behavior and molecular transitions. Another model imagined that the comet's nucleus contained regions of material that stored charged particles during periods of high solar wind activity and released them slowly when external conditions calmed. Such storage could create faint electromagnetic interactions detectable as resonance waves. A more speculative model considered the interaction between the nucleus and the vacuum itself. Under this view, the comet's materials could respond to tiny fluctuations in the local vacuum environment, expanding or contracting in ways that reflected interstellar conditions rather than solar influences. This concept, while not fully grounded in known physics, arose because the comet's behavior aligned with processes rarely observed in the heliosphere. Its interior seemed tuned to forces operating at thresholds seldom encountered by natural bodies that formed within the solar system. As debate expanded, researchers revisited seismic-like data hunting for deeper clues. When the pulses were examined across extended time windows, they displayed faint shifts that suggested long-period oscillations within the core. These oscillations, though subtle, pointed toward interactions between layers with different densities or compositions. If the interior served as a slow-moving system of overlapping structures capable of storing energy in tension, then releasing it through gradual shifts, the resulting cycles could explain much of the surface and coma behavior observed so far. Slowly, a new idea crystallized. The nucleus of 3I Atlas was not a static body. It was dynamic. The interior did not sit dormant unaware of the space around it. It responded, it adjusted, it equilibrated. And through these responses, the comet expressed its internal architecture in ways faintly visible to distant observers. The dust flows, the thermal gradients, the resonance cycles, the plasma irregularities, and the distortions in surrounding space all pointed to deep processes unfolding inside the comet. The interior whispered its presence through every subtle fluctuation. For researchers, this whisper was both revelation and invitation. It revealed a body not shaped solely by its past, but shaped also by the interactions it continued to experience. It hinted at a structure forged through countless cosmic environments, each leaving traces within the core, and it invited deeper inquiry, urging scientists to look beyond surface phenomena and into the quiet depths where the comet's true nature waited. The pulse beneath the core. As attention moved deeper into the enigma of 3I Atlas, the existence of an interior pulse grew more difficult to ignore. It did not resemble traditional periodic activity or rotational modulation, nor did it stem from the chaotic expulsion of jets, which had been conspicuously absent since the comet began its passage through the inner solar system. Instead, the pulse seemed woven into the nucleus itself, a slow and persistent rhythm that shaped phenomena across multiple observational channels. Its emergence marked perhaps the most revealing phase of the investigation, for it signaled not merely irregularity but coherence. The first unmistakable sign of this underlying pulse came when long-interval photometric series captured brightness oscillations too smooth to be attributed to surface scattering alone. These oscillations formed soft arcs across the data, rising and falling, with a stability rare for cometary light curves. When researchers filtered out all known environmental influences, the oscillations retained their structure. Their persistence implied that the fluctuations originated from within, reflecting a transition of energy through the interior. This impression deepened when instruments monitoring plasma density detected subtle, periodic compressions in the ionized materials streaming away from the nucleus. These compressions appeared faintly at first, but as 3I Atlas advanced into a calmer region of the heliosphere, their spacing became more pronounced. They followed an intricate cadence that matched neither solar oscillations nor particle streams. Instead, they reflected a slow, measured pressure cycle, arising as if from deep inside the object. The plasma responded in narrow ripples as though receiving quiet impulses transmitted through layers of material out toward the surrounding environment. Multiple wavelength observations added new layers to the puzzle. Ultraviolet sensors recorded faint shifts in emission strength, emerging from molecular groups sensitive to internal excitation. These shifts followed a pattern similar to the plasma compressions, suggesting that the same internal process could influence both molecular states and the behavior of charged material. The alignment did not fit any known sublimation pathway, Instead, it hinted that the nucleus underwent recurrent rearrangements in temperature density or internal structure that reverberated outward. Thermal maps of the nucleus added further complexity. During periods when the pulse grew stronger, heat distributed itself across the surface in low-amplitude waves that migrated slowly across the crust. These waves did not track the sun's movement. They originated independently, spreading in patterns that mirrored the cadence seen in plasma behavior. The heat diffused through the surface in ways that suggested organized pathways existing beneath it. The comet appeared to possess channels or materials that responded rhythmically to internal tensions. In a separate domain, polarization measurements detected a periodic reorientation of surface particles. The reorientation occurred in narrow intervals and shifted back again as the pulse subsided. The shifts did not arise from surface winds or dust flows, neither of which exist in vacuum. Instead, the surface itself seemed to adjust minutely in response to the oscillation. These adjustments could indicate that internal stresses propagated outward, with a regularity absent from typical cometary evolution. Dust velocity studies offered additional confirmation. During the strongest intervals of the pulse, dust grains escaping the nucleus gained tiny increments of acceleration. These increments repeated with a consistency that echoed the timing seen in ultraviolet emissions. The grains did not surge outward in bursts but drifted in soft accelerations that reflected a quiet expansion deep below. If the pulse altered pressure conditions within subsurface cavities, it could guide dust release with a delicacy not seen in solar system comets. Radar measurements further enriched the picture. When reflections were compared across successive pulse intervals, the internal structures revealed by subsurface echoes shifted slightly. These shifts formed patterns that circulated through the interior, hinting at movement or rebalancing between layers. The changes did not imply large-scale motion but gentle rearrangements of density or alignment. Layered material within the nucleus appeared to soften and tighten in slow cycles, creating subtle echoes detectable only through high-precision radar. At the same time, deep space communication arrays identified faint phase perturbations in signals passing near the comet. These perturbations aligned with the timing of the pulse and suggested that the surrounding plasma environment altered its structure as the oscillation strengthened. Even the region of distorted space surrounding the comet, previously mapped through refractive measurements, showed slight amplification during peak intervals. These effects, though small, provided evidence that the pulse radiated outward, influencing the space around the comet in measurable ways. With these observations, the pulse began to resemble not a singular anomaly, but a foundational mechanism binding several aspects of the comet's behavior. The interior appeared to act as a system wherein energy pressure and material properties shifted collectively. Such collective shifts could account for the synchronized fluctuations seen across light dust plasma and temperature. The nucleus behaved as though composed of interconnected zones that responded in unison to internal changes. A number of interpretive paths emerged to explore this behavior. One conceptual track imagined the pulse as a long-period relaxation cycle within a layered core where deep strata underwent slow compressions and expansions shaped by ancient structural history. A separate possibility envisioned the movement of stored energy between subsurface compartments, creating waves that propagated outward in controlled sequences. Another scenario placed the pulse within the long-scale interaction between the nucleus and the vacuum environment, suggesting that the materials might respond to imperceptible fluctuations in local vacuum pressure accumulated over cosmic time. Though the true origin remained just beyond grasp, what became increasingly evident was that the interior harbored a rhythm that had not formed recently. Based on the consistency of the oscillations, the pulse appeared to have existed long before the comet entered the solar system. It likely developed over millions of years as the nucleus passed through diverse cosmic environments. Each region could have left subtle imprints on the interior shaping materials that now responded with a quiet, almost meditative continuity. The interior pulse also began shedding light on previously unexplained behaviors. The strange curvature in the dust tail, the stable symmetry of the coma, the persistent distortions in surrounding space, and the faint resonances detected across multiple channels all found potential roots in the rhythmic activity within the core. The pulse acted as a unifying thread weaving together phenomena that had seemed disparate when viewed separately. Perhaps most compelling was the sense that the comet's internal processes did not simply react to external forces, they anticipated them. When 3I Atlas encountered regions of reduced solar wind turbulence, the pulse often intensified as though responding to the quieter environment with greater clarity. When solar conditions shifted, the pulse altered in ways that reflected not stress, but accommodation. The object behaved like a system with its own internal equilibrium, adjusting gracefully rather than chaotically to external conditions. As the comet continued its journey, the pulse remained steady, marking time in slow arcs, detectable only to those instruments capable of tracing its faint signature. For the observers charting its path, the pulse proved to be more than a curiosity. It was a window into the deeper architecture of 3I Atlas, revealing a structure built not from randomness, but from processes accumulated across cosmic epochs. The core whispered again and again through the oscillation, inviting a deeper understanding of a body that defied the simplicity once attributed to it. And with each cycle, it drew the scientific community closer to the realization that the mystery of 3I Atlas would not be solved by surface observations alone. Its truth lay within, carried in the silent heartbeat of a traveler shaped by distant worlds. The unraveling geometry. As the comet drifted deeper into the inner solar system, its surroundings began to reveal structures that had not been visible in earlier stages of observation. These structures did not emerge as physical objects or clouds, but as patterns hidden within the arrangement of dust plasma and reflected light. It was as though the space around 3I Atlas possessed a geometry of its own, a geometry that began slowly to unfold under the scrutiny of increasingly sensitive measurements. What emerged carried none of the jagged unpredictability typical of chaotic cometary environments. Instead, the patterns held a quiet cohesion, suggesting the presence of underlying order shaping the region. The first glimpse of this hidden geometry came when high-resolution imagery revealed faint concentric ripples extending outward from the nucleus. These ripples, almost invisible to the naked eye, formed arcs that intersected at elegant angles. They were not shock fronts or debris waves. Their spacing and curvature followed no known mathematical form associated with natural comet activity. When processed through advanced filtering, the arcs became clearer, revealing that the ripples expanded evenly in certain directions but remained compressed in others, creating a shape that defied simple interpretation. Soon after, instruments measuring the polarization of scattered sunlight detected subtle shifts that traced narrow corridors of alignment through the dust. These corridors twisted and curved, forming shapes reminiscent of flows within crystalline structures. They did not follow the direction of solar radiation, nor did they correspond to the comet's rotation. Instead, they traced a path that appeared to emerge from deeper processes within the nucleus. Their consistency suggested that dust grains experienced forces guiding their motion through space in ways that reflected a hidden order, as though the comet projected a faint lattice that influenced particle orientation. Meanwhile, plasma instruments monitoring the comet's wake detected elongated filaments of charged material that extended farther than expected. These filaments arranged themselves in narrow bands that curved gracefully as the comet moved forward. Their behavior hinted at a complex interaction between the dust, the comet's internal pulse, and the solar wind. The filaments shifted with an internal logic that did not resemble turbulence. Their stability implied the presence of a faint controlling influence that shaped the flow of ionized material. At the same time, light passing near the comet experienced slight angular distortions that suggested the presence of refractive boundaries. These boundaries did not behave like optical artifacts caused by dust clouds. Instead, they formed moving curves that rippled through the space around the comet. When mapped, the curves connected to the plasma filaments and dust corridors, forming an interconnected geometry that shifted with a rhythm resembling the internal pulse already identified within the nucleus. The distortions appeared to trace the steps of an unseen choreography, suggesting that the comet's surroundings moved in response to patterns originating deep inside. As researchers examined these effects, they noticed that the geometry exhibited layers. The innermost layer consisted of rapid fluctuations in dust alignment and brightness, forming thin spirals that clung close to the nucleus. Farther out, a broader structure took shape within the coma, forming looping arcs bound by the timing of the pulse. Beyond the coma, the plasma filaments extended into space like faint tendrils marking the outermost layer of the geometry. Each layer moved in harmony with the others, forming a multi-tiered structure, integrating dust gas and electromagnetic behavior into a single evolving system. The geometry became even more intriguing when analysts compared it to changes in the comet's thermal signature. During intervals, when the internal pulse intensified, the geometry expanded. Dust alignment corridors widened, plasma filaments grew longer, and refractive curves extended farther from the nucleus. When the pulse weakened, the geometry contracted. The expansion and contraction followed a steady cycle that resembled a slow breathing pattern, manifesting in space itself. For those analysing the data, the geometry no longer appeared accidental. It behaved like the outward expression of deeper processes shaping the comet from within. In parallel with these observations, spectroscopic analysis revealed that the geometry influenced how molecules within the coma distributed themselves. Molecules associated with high-energy states clustered along specific corridors of the structure, while more stable compounds accumulated in quieter regions. This distribution defied the usual chaotic mixing of gases within cometary comas. Instead, molecules appeared to follow pathways shaped by underlying patterns, as though guided by an invisible gradient within the geometry. Such behavior suggested that the interior's rhythm extended its influence beyond dust and plasma, shaping even the arrangement of molecular species. Temporally, the geometry displayed a curious modulation. During certain orbital alignments, the entire structure shifted, slightly changing orientation relative to the Sun. This shift did not correspond to gravitational effects or solar radiation pressure. Instead, it hinted at the possibility that the geometry responded directly to the interaction between the comet's internal state and the larger heliospheric environment. The modulation's timing carried a sense of anticipation, as though the geometry adjusted itself to external conditions before they arrived, aligning with the quiet adaptability that characterized the comet's behavior. To explore the phenomenon further, computational astrophysicists constructed models using layered dynamic fields that mimic the behavior of interconnected systems. Although the models captured fragments of the geometry's expansion and contraction, they failed to replicate its coherence. The real geometry moved with a subtlety that eluded synthetic reconstruction. The models produced shapes lacking the multi-tiered depth found around 3I Atlas. These shortcomings highlighted the possibility that the geometry reflected interactions between materials and fields shaped over long cosmic histories, processes beyond the reach of current theory. A particularly compelling discovery arose when deep space antennas tracked signals crossing different parts of the geometry. Signals passing through regions aligned with the dust corridors exhibited slight phase shifts, while signals passing through the plasma filament regions displayed subtle diffraction patterns. When combined, these effects created a soft mapping of the geometry, allowing researchers to visualize the structure in unprecedented detail. The map revealed a network of curves and threads that extended outward in patterns too delicate for direct imaging, but too consistent to be ignored. As this mapping progressed, a broader realization took shape. The geometry was not static. It grew and diminished in quiet cycles following the cadence of the interior pulse. In moments when the pulse intensified, the geometry unfolded like a flower opening in slow motion. When the pulse softened, the structure retreated, pulling its arcs and filaments closer to the nucleus. This dynamic quality gave the geometry an organic sensibility, though rooted in physics rather than biology. It behaved like a field shaped by ongoing transitions within the core. In the final analysis, the geometry presented the clearest indication yet that 3I Atlas was not simply an object forged from random collisions and frozen volatiles. It carried within it a layered architecture shaped by interactions spanning vast cosmic distances. Dust plasma light and molecular behavior all moved within patterns too cohesive to originate from external forces alone. The geometry was the comet's quiet testament, revealing a system guided by slow internal rhythms that had persisted for epochs. For the observers charting its progress through the solar system, the unfolding geometry carried both wonder and challenge. It hinted that the comet's mysteries reached outward from its core, shaping the very space around it. It suggested that the object's internal structure not only survived interstellar travel, but expressed itself through every surrounding medium. And it marked the beginning of a deeper inquiry, one that would reach beyond surface irregularities and into the very principles that shaped 3I Atlas across its long journey through the galaxy.